Hello grade 12s and welcome to this video. In this video, we are going to be working on KZN's Mathematics Common Test for March 2020. So this test is for 100 marks and it is 2 hours. I also want to mention that I got this paper from stanmorephysics.com, which is a high school website where they upload a whole lot of past exam papers from maths to physics, all the way from grade 8 to grade 12. So you can use that as a resource to help you practice. Okay, so remember that this is just a preparatory video really for your March exam this year, 2024. Okay, moving to the instructions, just remember that you need to round off to 2 decimal places unless stated otherwise. And also remember that the diagrams are not necessarily drawn to scale. So if something looks like 30 degrees, it doesn't mean that it's 30 degrees unless you can actually prove that it is 30 degrees. Okay, so with that being said, let's move on to the first question. Okay, question 1 says, given the quadratic sequence, P, and then we have 5, Q, and 19, 1.1 says calculate the values of P and Q if the second constant difference is 2. Okay, they told us the second constant difference. So let's actually write this out and see what we're going to have. You see, we have P, then we have 5, and then we have Q and 19. And they want us to find out what exactly P and Q are going to be if the second constant difference is 2. Well, how do we find the second constant difference? We'll find it first of all by finding the first difference. So the first difference, we can start over here. We would say 19 minus Q. That's what's going to give us that term, okay, between those two terms in the quadratic. So 19 minus Q, that's what we get there. And then this side will say Q minus the 5. So Q minus 5, that's our next term there. And then we'd say 5 minus P, 5 minus P. So this right now is our first difference, right? It's not constant. And now they told us that the second constant difference is 2. So let's go ahead and find the second constant difference. The second constant difference we will find in the same way. We will just say 19 minus Q minus Q minus 5. So let's see, 19 minus Q minus, but do you notice that Q minus 5 is 2 terms? So it means you need to include brackets so that it can multiply and it can apply to the Q and the negative 5. So we're going to have Q minus 5. Okay, and that's what we have there. Then we should also do the same to these 2 terms as well. So Q minus 5 minus the 5 minus P. So we'll include brackets and then say 5 minus P. Okay, so you see what we got here, right? That constant difference, that second constant difference, because that's what we just found. And this second constant difference, there's something we know about the second constant difference, is that it is constant. So it means that whatever number that you have here is the exact same number that you'll have here. The second constant difference will always stay constant. It doesn't change. So immediately I'm already going to say, oh, okay, these two are equal. Okay, so let's see what we can do with this. I could have tried to equate them, but the issue is you have a Q here, you have a P here, and here you have Q and Q. So because you have 2 letters, it's not a very good idea to just equate them because you will not be able to solve for P or Q, okay? So let's use what they told us here. They told us that the second constant difference is 2. Well, this thing that we have here, like 19 minus Q minus 5, that is the second constant difference. And even this one is the second constant difference. So it means that each of these, right, they're both equal to 2. But which one are you going to use? Are you going to use this expression or this one? Well, you see, this expression has Q and P. That will not help you to solve for one of it. So first, we have to use this one. The reason is because it has Q and Q, right? Because it only has Q as a variable, we can easily solve for Q. So this is what I'm saying. Because we've found the second constant difference, I'm going to take one of the second constant difference, that is 19, minus Q minus, and I'm just going to expand and distribute that really. That's negative q and plus 5, right? That, I'm going to say that that second constant difference is equal to 2 because that is the second constant difference of this pattern. And then now I'm just going to simplify and really just solve for q. So I'm saying 19 plus 5, 19 plus 5, that's going to give us 24. And then negative q minus q, that's going to be negative 2q. And that is equal to 2. Now you can see we can just solve for q. So I'm going to take this over because it's negative. So that becomes a positive 2q. And then we still have 24. And I'm taking this 2 over. And that becomes a negative 2. So really we just have 22 is equal to 2q. Then if you divide both sides by 2, it means that q is actually equal to 11. 22 divided by 2 is 11. Okay, so there we found q. Now how do we find p? Well, we could just go ahead and use whatever second constant difference has p in it. This expression, this is a second constant difference and it has p. So I'm again going to say that q minus 5, and I'm just going to distribute that out quickly. So that is a negative 5 when it multiplies to the 5 and becomes a positive p when it multiplies to that negative p, right? That expression is equal to 2. But the good thing is I know what q is. Q is 11. So I'm going to, in place of q, say 11. So 11, and then we have minus 5, which is minus 10, and then plus p is equal to 2. 11 minus 10 is 1. So p is equal to, we still have a positive 1 here, and you still have 2 here, right? So this positive 1 can come over and become a negative 1. And so p is actually just equal to 1. So there we go. Q is equal to 11 and P is equal to 1. Okay, so that's the first question. Moving on to the next question. Okay, so the next question 1.2 says, determine the nth term of the quadratic sequence. So remember, this was the quadratic sequence, but we now know what P and Q are. So P is 1, so just replace that, that's 1, and Q is 11. So how do we find the nth term? How do we find the general formula, okay, of this quadratic sequence? Okay, we can just say 19 minus 11 to get the first differences first. 19 minus 11, 9 minus 1 is 8, so that is 8. And then 11 minus 5, that's going to give us 6. And then 5 minus 1, which gives us 4. So that's our first difference. Then we get the second constant difference, which we know is 2 already. So you could have also just said 8 minus 6, that's 2. And then that's also 2. So now that we have this, we can go ahead and find the general formula. The general formula is found by saying, you see all of these first terms in each of these rows, right? We're going to equate them to the following. The 2, you're going to equate it to 2a. 2a is equal to 2. And then the first term here, you're going to equate it to 3a plus b, okay? And then this one, you equate it to a plus b plus c. So this is just something that you have to remember when working with quadratic patterns. Okay, so we have 2a is equal to 2. So 2a is equal to 2. If you divide both sides by 2, a is going to be equal to 1. So we have a. Now to get b, you can say 3a, but I know what a is. A is 1 plus b is equal to the first term, which is 4, right? And so I'm saying b is equal to, I still have the 4, and I'm saying 3 times 1 is 3. So I'm taking the 3, positive 3 over, and becomes a negative 3. B is equal to 4 minus 3 is 1. And then here we have a plus b plus c. But we know what a is. A is 1, b is 1, and c is just c, is equal to 1. Okay, so it means that 1 plus 1 is 2. So I'm saying c is equal to, I still have this 1 here. This is a positive 2. It comes over and becomes a negative 2. So c is equal to 1 minus 2, which is negative 1. So it means that our Tn formula, remember, it's in the form of an squared plus bn plus c. So it's going to be Tn is equal to, since a is 1, you don't have to write that 1. You can just say n squared. Likewise with b, since b is 1, you don't have to say 1n. You can say plus n. And then c is negative 1, so minus 1. And this would be our Tn formula for that pattern. Okay, so that is the nth term of the sequence. Moving on to the next question. Okay, question 1.3 says, determine the first term of the sequence that will have a value greater than 10,301. Okay, so in this question, this word first term can be a little confusing, but when they say first term in this particular question, they're not referring to that A value. Okay, so that's not what we're speaking about here. The question really is saying, which term, right, in this pattern, what will be the first term in this pattern that will have a value that is greater than this number, 10,301. So this is really what's going on. You have terms, right? So of course I have term 1, term 2, term 3, term 4, and this can keep going, right? That's the term numbers. Then these terms have values, right? We already know the values of the first 4 terms, 1, 5, 11, and 19. These terms have values. Now, the question is, which term, what will be the first term that will have a value greater than 10,301? So you see, they're not necessarily asking which term has a value of 10,301. No, they're asking for which term will have a value greater than 10,301. What is the first term that will be bigger than this number? So that term will be after whatever this term is, right? That term will be after this one, right? Because of course this thing is increasing. It just depends really, because then again it is quadratic. So how can we actually find the answer? Well, to construct a way to find it, this is what we can do. Because they're asking, right, determine the first term in the sequence that will have a value greater than this. They want which term will have a value greater than this. So since they're speaking about terms, we can use the Tn formula, because the Tn really tells us the value of your term. So we're trying to find out in this pattern, which term value, right, is bigger than 10,301. And then we can just solve for this inequality first. Okay, so Tn we already found that in the previous question. It is n squared plus n minus 1. So n squared plus n minus 1 must be greater than 10,301. Then we can just go ahead and say n squared plus n minus 1, and then we're going to take this 10,301 over and it becomes negative 10,301 is greater than 0. And so this is n squared plus n, and when you subtract these, it's just going to give you negative 10,302, okay, because it became even more negative. And this must be greater than 0. Okay, then you see we have a quadratic inequality and we have to factorize this quadratic expression. I know that this can be it may take long to factorize. So something you can do, well, I used to still factorize it as this. I'll say 10,302, right? Then I'll say is equal to, and I say shift and factorize, just so that I can see all the factors and see what gave this number. So then I see 101, right? So I could just try this and say, okay, fine. What is 10,302 divided by 101? And I get 102, and it already worked instantly. So I get 102 because you see 101 and 102 as factors, right? When you multiply them, they give you 10,302. But you see that there are also factors of this that can help to give you this coefficient of positive 1 in the middle, right? When you're factorizing. So they would work perfectly. But remember, it needs to be a positive 1 because that's the coefficient of n. So you need to leave this one positive and make this negative, because 102 minus 101 is going to be positive 1. So our factors is really just going to look like this. You have n and you have positive 102 and n and negative 101, and it's greater than 0. That's one way of doing that, right? Then there's the other way where you could have just used the quadratic formula, okay? So the quadratic formula, you would just put it down. I will just not really write it down here. Don't actually write it down. If you write it down, it's like you didn't factorize. So I'm just going to say negative b, and I can see that b here is the positive 1. So negative 1 plus minus, so I'll just say plus, the square root of b squared, which is 1 all squared, minus 4 times a, which is an invisible 1 that we have there, and then times c, which is this negative 10,000 and 2. So negative 10, 302. And then I'll say over 2a, and a is really just 1. So you can say times 1, it's okay. But even if you didn't, it was still going to work out. Do you see that you get 101? Now, you're going to have to be careful how you take that. That would be a situation where you do not have your factors yet. This is the answer, okay? It's the value of n when you're trying to factorize this using the quadratic formula instead of normally. And so you got 101, right? That's the answer. And of course, if you change the sign to a negative, because remember it says plus minus there, it gives you negative 102, meaning n is equal to negative 102. But when you put this down as an answer for your factors, you need to say it like this. You see, it's the same thing as taking 1 over 1 over the equal to sign. And now you have n minus 101. That's your first factor, n minus 101. And then this one, taking the negative 1 over 2 over, and so you have n plus 102 as your second factor. Okay, so that's how to use the quadratic formula to do that if the factors were like really big and they just looked, complicated. Or you could have also done it the other way that I did. Okay, so this is what we have. And we can now finally find the values of n. Now, because it is an inequality, you're going to have to either use the number line method or use a graph method. I'll use both methods because this is a March paper. So I do expect that it's new grade 12s that are maybe watching this video. Maybe you're used to a grade 11 method of working this out. So I'll work this out through two methods. The number line method of simplifying or solving for an inequality is like this. So you're going to take down what we will call our critical values. And our critical values are really just like if you have a factor n plus 102, your critical value of n is going to be the same thing as you taking 102 over the equal to sign, and it becomes a negative 102. Okay, so that one is negative, so it'll go here. So we have first the negative 102, right? And then the second factor that we have is 101. So if you take n and is equal to, and you're taking negative 101 over the equal to sign, it becomes a positive 101. So you have 101, right? So I'll put a circle on top of both of them because I'm just trying to decide where they're going. So to solve for this, what you can do is you can think about a number that is less than negative 102. So first of all, let's think about that. A number less than negative 102 can be negative 103. And then think about a number greater than negative 102, which can be negative 101. Okay, not the same as that number. Let me actually even push that. And then we're going to do the same for this number over here, 101. Take a number that is less than 101, which can be 100, and then a number greater than 101, which is 102. And now, in order to find out how these inequalities are going to look, we're going to do this. So you can go ahead and place down, I don't even have to put that like that. I can just say n and my negative 102 and n and my positive 101. And I'm just going to really solve for the inequality when I find out where the arrows will go. And this is how we're going to find out where the arrows go. So let's start with the negative 102. With the negative 102, let's try substituting negative 101 into this expression. And when you substitute it into this expression, it should give you a value greater than 0, because that's what the inequality says. It wants you to find the values of n for which this expression will be greater than 0. So I'm going to substitute negative 103 into this expression, and if it gives me a value greater than 0, then it works. Okay, so I substituted negative 103 and that works. It gives me 204, which is a value that is greater than 0. So since this number worked, what I'm saying is that numbers going in this direction are working for this inequality. And the numbers going in this direction compared to negative 102, these are values that are less than negative 102. So how I'm going to answer this is I'm saying n needs to be less than negative 102. And see, the arrow actually helps you with the inequality. Do you see that? They have the same shape, okay, in the same direction. Okay, so that's that one. That's solved. And then, of course, this side, you do the same thing. So you can try 100 if you wanted. If you tried 100, look what would happen. That is 100 and 100. And look at what we get. We get a negative number. So you see that 100 is not working for this, okay? So it means that the answers in this direction are not really working. So let's try 102 for this critical value of 101. If you change that to 102 instead, this is what we get. We get a positive number, 204, okay? So it's going that direction. So it's going in this direction. And so these are values that are what than 101. These are values that are greater than 101. So you can say n is greater than 101. Again, that arrow really helps you with the inequality. So do you see now that this is the first way you could have solved for that? Of course, we will go back into detail of actually solving for n. So this is a method regarded as the table method when you are solving for inequalities, quadratic inequalities specifically. You can use this method, or you can use the method that is mostly used in grade 12, which is the method I'm about to show you. Now, with the grade 12 method, I'm going to still leave this here because we already have our critical values. So the grade 12 method, we will look at this, right? This expression. And if you think of this expression as a graph, what kind of graph is it going to form? A parabola. It will form a parabola. And it's specifically a parabola that is a smiley face because, as you can see, the coefficient of a is 1. It's a positive number. So this is what's going on. You're going to have a positive parabola like that. Then you draw an x-axis. And now that we have this, we're just going to put down our critical values, just like we found in the previous part when I was explaining that. So the first critical value is negative 101. So negative 102, sorry. And the second one is positive 101. Now that we have that, we would just find out for which values of n would this graph be greater than 0. So here's the rule that you can think about when you see that. You see, it's kind of like there was a y-axis. I don't really need the y-axis. And this is actually saying that you need to find the values of n for which its y values will be greater than 0. So let's think about where would we have y values greater than 0? Well, this is our y-axis. The only place that you have y values greater than 0 is over here. Everything here is less than 0. So you will only be looking at parts of this graph that has y values greater than 0. And look at where that's going to be. See this graph? This has a y value greater than 0. That point over there. Okay, this point has a y value greater than 0. But when you go down here, this has a y value less than 0. So we can't use that. So now do you see that if you monitor this graph all through, you would notice that the only places with y values greater than 0 is over here. Everything that is above the x-axis. So this is something you can just remind yourself about. If you see that the expression is greater than 0, if you're using the graph method, just know that when you're looking for greater than 0, you only look for parts of the graph that lie above the x-axis, okay? And then, of course, if it's less than 0, it's below the x-axis. So what we're just going to do here is find the parts of the graph above the x-axis, which we saw was this. That part of the graph is above the x-axis, and this. Everything here is below the x-axis. We don't include that. So now we're just going to really speak about what the n values are for these highlighted parts. If you line this down to the x-axis, look at these. Look at this number. Since this over here is 102, negative 102, look at these numbers. The parts of the graph that has a positive or positive y values, they are values that are moving towards this direction. These are values that are less than negative 102. That's why we again would have said n is less than negative 102. And then we'll do the same to this part. You see, this is the highlighted part. The part that is greater than 0 has a y value greater than 0. Line it down to the x-axis. You see that it's moving in this direction. So that's where n is greater than 101. And so that's how you solve that using the graph method. Okay, so those are the two ways of solving for that. I'm only going to use those two ways probably in this paper only. In the other papers, the other March papers, I probably will not. I will reference this paper though so that you can see how that works. Okay, so all in all, we know that n must be less than -102 but greater than 101. Now, we cannot accept this answer. And the reason why we cannot accept it is because the n values here are negative. You see, your term number cannot be negative. Your term value can, okay? So for example, term 1 can be equal to -25. That's fine, that's normal. But you cannot have something like term -1, okay? And the reason why is because these numbers are seen as positions, okay? Positions are anything that you can count, things that move forward and you count, like days, for example. I can say day 1 and day 2 and day 3, but I cannot say day -5. We're not time traveling backwards. So you do not have negative positions. Okay, so we cannot take the negative values, meaning we only have to concentrate on this. But let's go back to the question and just make sure that we are actually answering their question. The question says, determine the first term of the sequence that will have a value greater than 10,301. What is the first term? Which first term will have a value greater than this? Now, you see 101, the term 101. What value does it have? If you take 101 as an n value, right, as a term value, and you substitute it into this Tn formula, you will literally get 10,301. So it means that term 101 is equal to 10,301. But we need a term that is going to be greater than this. So think about it. Since term 101, right, is 10,301, the first term, the very first term that will be bigger than this number would be the term immediately after term 101, which would be term 102. Okay, be very careful to answer their question. Yes, I know that n is greater than 101, but they want a specific answer. That's why they say determine the first term of the sequence that will have a value greater than term 10,301. So that term, I'll say, therefore, that term is equal to 102 because term 102, that term will have a value greater than 10,301. Okay, so that is that answer. I took a bit long on it because I just wanted to explain two ways of doing this. Okay, moving on to the next question. Okay, so we're on question 2 now, and question 2 says, the sum to n terms of an arithmetic sequence is 36. Okay, so the sum to n terms, meaning you're counting a specific amount of terms, but we don't know how many they are. That's why they're saying the sum to n terms, the sum of n terms really, okay, of an arithmetic sequence is 36. Then they also tell us that the first and the last term are 1 and 11 respectively. So it means the first term, T1, or you could call that A, that is 1, right? And the last term, which you can call Tn, or you could call L, right? That is 11. They want you to just determine the common difference. That's all. Okay, so to find this one, since we know A and we know the last term, I was thinking, how about we use this formula, the sum of an arithmetic sequence formula that says Sn is equals n over 2 multiplied by A plus L, right? But how will this help us? Well, we don't know what n is. So we could use this formula to first find n. But at the end of the day, we need to find the common difference. The only sum of terms formula of an arithmetic sequence that includes that common difference is this one. Sn is equal to n over 2, open bracket 2a plus n minus 1, multiplied by d, right? That one. Now, the thing about this is, it seems as if both of them will be helpful in this. And this is for 5 marks, so it makes sense. Both of them will be helpful because in this one, we have A and we have L, right? We have A and L, which you can substitute there. And if we do that, it would help us, we already know that Sn is 36 as well. It will help us to solve for n. Okay, we'll be able to find what exactly the value of n is. Then we can take that and substitute it into here. So again, we'll substitute what Sn is, what A is, and when we substitute what n is, we'll be able to find out what d is. So you see, in this case, both formulas would probably be useful. Okay, but in this method, what we can just do here is say Sn, that is 36. So 36 is equal to n. We don't know what n is, so just say n over 2. And then A is 1 and L is 11. So 1 plus 11 is 12. So we have 36 is equal to n over 2 times 12. If you like, you can try and get rid of that 2 by multiplying both sides by 2. Right, and when we do that, what we get is 72 here is equal to, and here the 2 cancels out. And now you have n times 12, which is 12n. You could have done that, okay? Or you could have also just multiplied this fraction by this. Okay, but now we have this, and we can just go ahead and divide both sides by 12. So divide by 12, and so n is finally equal to, this is going to be 6, okay, because we have 60 divided by 12 is 5, so 72 is 12 extra. So n is equal to 6. And now that we have n, we can use it in the second formula. Okay, so we have that. So we can finally say that S of 6 terms, we now know what n is, it's 6. S of 6 is equal to, we're saying 6 over 2, and then open brackets 2a, a is 1, plus n minus 1, which is 6, minus 1, multiplied by d, which we don't know, and we're just going to keep that open. Multiply by d like that, right? Now we know what S of n is. We know it's actually the sum of 6 terms. So in place of S of 6, we know that that is 36. Okay, S of 6 terms is 36. So 36 is equal to 6 divided by 2, that is 3. And then we can just simplify what we have here. So 2 times 1 is 2. And then we have 6 minus 1 is 5, which has been multiplied by d. So that gives you positive 5d. And then we can just go ahead and get rid of the 3 by dividing both sides by 3. 36 divided by 3 is 12. And then we have this, because the 3 cancels, so we just have 2 plus 5d. Okay, then we can take the 2 over. When you take the 2 over, it becomes a minus 2. So that's 12 minus 2, which is 10. 10 is equal to 5d. And then if you simplify, just divide both sides by 5. D is finally just equal to 2. So there, that's one way that we could have done that. That's method 1. See, using both formulas. So the next question is question 3. And as you can see, it's a proof. This is a proof that could come in, okay, depending on wherever you're writing from. So this is a proof that you should just try to study and make sure that you know. Also make sure you study the arithmetic proof as well. Study both of them, because any one of them could come in your exam. Okay, so this is what we have. In a geometric sequence, the first term is A and its common ratio is R. Prove that the sum to n terms of the sequence is this. So we're just trying to find the sum to n terms. So just proving that is actually equal to this. Okay, so this is how we will prove that. We're going to first of all start by saying S of n, right, is made up of, because I'm saying the sum of n terms, meaning we are adding terms up together from the first term. The sum of n terms is equal to term 1. Starting from term 1, you add term 2, you add term 3, and you keep adding all the way to the last term, which we call Tn, right? That's our formula really. Now, do you remember that the first term, we actually call that something else. We call that A, right? So I'm really just saying Sn is made up of A. Then plus, how do we get the second term? Well, let's think about it like this. You know that the Tn formula of a geometric, because it's geometric, of a geometric sequence is A multiplied by R raised to the power of n minus 1, right? So since this is the Tn formula, T2 Even if you substitute a t1, you'll see it simplifies to a. But term 2 is equal to, if we're going to say a multiplied by r raised to the power of, in place of n, we're substituting 2 because we're trying to find what term 2 is. So 2 minus 1. 2 minus 1 is 1. So it means that term 2 is actually equal to a multiplied by r raised to the power of 1, which you don't have to write. So it's really just a multiplied by r, which I'm just going to write as a times r. That's the second term. Then the third term you would find by, if you also just did that, you'd see that a multiplied by r to the power of 3 minus 1 is really just a times r raised to the power of, what is 3 minus 1? 2. So that's a r squared, right? That's what we have, a r squared. And if you keep going, we're going to have ar cubed and then ar to the power of 4. And that will keep happening, right? Now, what is the last term? Again, Tn is always equal to a times r raised to the power of n minus 1. So that's what that is. I'm going to just rewrite that there. So that is a times r raised to the power of n minus 1. Now, since we know what the last term is, you can even find out what the term before the last term is, what the second last term is going to be. And this is what it's going to be. Think about it like this. You see that when we were moving forward, the exponent on r kept increasing. The reason you have an a here is because the r, right, has an exponent of 0. Anything to the power of 0 is 1, and a times 1 is just a. And so here it was, the exponent was 0, and then an invisible 1, and then a 2, and then it will be a 3, and it just keeps increasing like that. Now think about when you're moving backwards, what's going to happen. If it's going to increase by 1 every time you move forward, when you move backwards, it's going to decrease by 1. So it means that this, the exponent in r right now is n minus 1, right? Since we're moving backwards, it's going to decrease by a 1. Making this, okay, since it's decreasing by 1, what's actually happening is you have a times r raised to the power of n minus 1 minus a 1, right? Which gives you a times r raised to the power of n minus 2. Okay, so that's what we're going to have over there. That's going to be the second last term. Okay, I'd actually like to work with it as just the first, second, and second last and last. So, okay, I think I'll just get rid of this, but it's fine. I can leave it there for reference. Okay, so that is what we're going to call our first equation. Now, in order to get the second equation, what we're going to do is we're going to take equation 1, right? That equation, and we are going to multiply that equation by r. Okay, to do this, you're going to do this to both sides of the equation. You're going to do this to the left and the right hand side. On the left hand side, you have Sn. You're going to have to say Sn multiplied by r, which we can just write as, that is going to be equal to Rsn. And then it's equal to. Now, in all of these terms, you're also going to multiply an r, because really we're taking all of this and we're multiplying it by r. So the first term gets multiplied by r. R times a is ar. The second term gets multiplied by an r. A times r is positive. We have ar squared. Let me just actually write that in red. Squared. Third term multiplied by r. That's going to be positive ar. We have squared times the r raised to the power of 3 instead. And this will keep happening, right? And we also have to do that to this as well, just to see what happens. The second last term, when you multiply that by r, what happens is you have a times r raised to the power of, now remember, when you're multiplying by an r, you're saying a times r raised to the power of n minus 2 multiplied by an r. Here, we're looking at the r's, right? The bases are the same and you're multiplying. So you need to add the exponents. The exponent on r here is a 1. So what's happening is you have a times r raised to the power of n minus 2 plus 1. That exponent gets added because they have the same base. And so negative 2 plus 1 is negative 1. That's what you have there. That's this equation's second last term. Then lastly, because we just multiplied only the r times, of course, this, then we have to multiply the r times that last term. Same thing is going to happen. You have an a times r raised to the power of n minus 1 being multiplied by r. Let me just write that r, right? And that, since it gets multiplied by r, there's an invisible 1 here. You have a times r raised to the power of n minus 1, and that 1 gets added here. Negative 1 plus 1 gives you 0. So what you have here is positive a times r raised to the power of n. And let me just write that r in red. Okay, so that's what we have so long when we multiply the first equation by r. So I can go ahead and just call this is equation number 2. We got equation number 2 now. Now, how we're going to simplify this is you're going to have to think about it carefully. Look at what they asked for. They want this formula to be formed. They want the formula that says a bracket 1 minus r to the power of n. Let me show you what happens depending on how you work this out. What we're going to do is we're actually going to subtract these equations. And the reason why is, as you can see, you have a minus in the middle. What happens is there was subtraction going on there. So we're going to take equation 1 or 2 and we're going to subtract it by the other equation. But you have to decide on which equation should be subtracted. And how you decide is by looking at the left-hand side of both equations. You see, the first equation's left-hand side is Sn. If you had to say equation 1 minus equation 2, let's see what happens. So minusing by rsn, right? Do you see that in this one, the r, right, is at the second term of this expression? So let's look at that. Does that fit this? Yes, it does. You see, you have 1 minus r to the power of n. The r is on the second term. So in order to make your equation to look like this, you need to say equation 1 minus equation 2. If you wanted the equation to look like this, because they could just, give you this formula in any way. If you wanted to look like this, a bracket r to the power of n minus 1 over r minus 1, then you would have to say equation 2 minus equation 1, because then you would have rsn minus sn. You see that the term with r is first, just like here. Term with r is first. Okay, so you're just going to have to think about that and see what exactly they're asking you specifically for. So in this, they're asking us for this one, so we're going to say equation 1 minus 2. Okay, so you're going to say equation 1 minus 2, and you need to do this on the left and the right hand side of both equations. So the first equation, equation 1 minus 2, okay, on the left hand side, that of course is our Sn minus our rsn, and now we're going to just find the other part. So it's equal to, and now again, we're saying equation 1 minus equation 2. You're going to look at the right hand side now. We're saying all of this is going to be subtracted by all of this. You see, if we're subtracting, and let's say you had a 2, right, plus 3 plus 4, and then on this side, maybe you had a 1 plus 2 plus 3. If I had to say this equation, right, let's say equation A minus equation B, what would cancel out here? Because I'm saying this minus this. Well, in this, what would cancel out is, first of all, when I reach the 2, this 2 is going to subtract by this 2 over here, so they would cancel. And when I reach the 3 would cancel out with the 3 here. Okay, and then you see what we're left with. That's kind of what we're going to try and do here. We're going to see what will cancel because we are subtracting. So really what you're just trying to do is see which terms do we have in the first equation, right, that are also in the second equation. And if you look at that, A, we don't have any A here. So it means that A will not cancel. It's safe. But AR, look at this. We have an AR here. So it means that this AR would cancel with this AR when you subtract equation 1 from equation 2. Then you see we have AR squared. AR squared would cancel with this AR squared when you subtract. Then you have an AR cubed here. After this AR squared, you would have had an AR cubed. That would have cancelled with this AR cubed. Okay. Then You see that here you have an AR raised to the power of n minus 2. If you think about the term that would have been before this one, since this is AR to the power of n minus 1, the one that comes before this would have been AR to the power of n minus 2, just like here. See, we had AR to the power of n minus 1, so the one previously before it is the one with n minus 2. So that's what we would have had here. So it means that this AR to the power of n minus 2 would cancel with that AR to the power of n minus 2. And then this AR to the power of n minus 1 would cancel with this AR to the power of n minus 1. And now this is the end of this equation. So nothing else will cancel. So what is left? Well, in the first equation, because we're saying equation 1 minus equation 2, what we have in the first equation is the A, right? That's what's left. So equation 1 minus what's left in equation 2. In equation 2, the only thing left is this AR to the power of n. So minus A times R raised to the power of n, and put in R in red. Okay, so this is where we are now. We're almost done with this proof. Now that we have this, we're just going to simplify. So this is Sn minus Rsn. We need to think about a way to simplify this expression. Well, we can simplify it by factorizing, taking out a common factor. Look at the left-hand side, right? What is common in this first term that is also in the second term? Sn. So we're going to take Sn out as a common factor. Then we open a bracket and say, what is left? Well, it's the same thing as saying, what did you multiply by Sn to get Sn? That must have been 1. Or you could have said Sn divided by Sn. That is 1. Likewise, I could also say the second term, negative Rsn divided by Sn. That would give me negative R. Okay, and then this is equal to, look at what you can do here as well. Do you notice that A and A are common in the first and second term? So take A out as a common factor. Again, A divided by A, that's 1. And then we have AR raised to the power of n divided by A. Okay, but remember you still have that negative there. So it's minus, it's kind of like the A's cancel and you have, so R raised to the power of n. Okay, so this is what we have. Now remember, the whole point is so that you can find Sn. Okay, so how do we make Sn the subject in this formula? How do we get this on its own? By getting rid of this. You see that this is being multiplied to Sn. So to remove it, you need to divide it. Okay, so divide both sides by the 1 minus R, the 1 minus R. And then that will solve the problem. And so this means that Sn is finally equal to, so this cancels here, that's why we just have Sn. And then we're just going to have A multiplied by 1 minus R raised to the power of n over 1 minus R. Okay, so that is how we find the proof of that. Okay, so you can go ahead and make sure you study this one and also study the other proof as well, the arithmetic one, the one that says n over 2 multiplied by a plus l. And of course, that also leads into this one, the 2a plus n minus 1 times d. You need to study both of them as well, okay? Because it may come in. Okay, so that is the answer for that. Moving on to the next question. Okay, so now question 3.2, look at what we have. We have sigma. I know when people say sigma, they get scared. Okay, but I'm glad for this first question because it really tells you what you're supposed to do before actually attempting to solve whatever question that they are giving you when it comes to do with sigma notation. Okay, so the question says, write down the first 2 terms of the geometric sequence if we have this. So you can see that they say the sum of this pattern with this formula starting at k being equal to 1 and ending at m. Okay, so we have to find the first 2 terms of the geometric sequence. Okay, so the first 2 terms, so you just have to expand it. You see that they say you need to start where k is equal to 1. So that's what we're going to do. Start at k is equal to 1. And we're going to take the formula and say 3 multiplied by 2 raised to the power of 1 minus, and then we have k. The first term is where k is equal to 1, so we substitute. And so our first term is going to be 3 times 2 raised to the power of 0. 2 raised to the power of 0 is 1. And then 3 times 1 is just 3. So that's our first term, 3. And then the second term, we'll find that by saying that was just T1. T2, we find by saying k being equal to 2. So again, it's just 3 times 2 raised to the power of 1 minus, but this time 2. And so term 2 is equal to 1 minus 2 is negative 1. And if you say 2 to the power of negative 1, it gives you a half. And a half times 3 is 3 over 2. Then again, you can just put it onto the calculator and you will see the answer. So those will be the first two terms. It's 3 and 3 over 2. Okay, moving on to the next question. Okay, the next question, 3.2.2, says calculate the value of m if, as you can see, it's the exact same thing, if the sum of this series is equal to this number. So we just have to find the value of m. Okay, so since we are working with a series and sigma is speaking about the sum, they're basically telling us that the sum from k being equal to 1 all the way to m is equal to this number. So first of all, let's just clarify this. You see, you always have to look at this. You always have to check this number over here, whatever number that this part starts from, right? Because this is where the series will start, okay? And that's where it ends. So you need to always check this. If it starts at 1, it's fine. You don't have to really overthink anything. If it didn't start at 1, you need to be careful to find out the amount of terms, okay? There's a very big difference between the amount of terms in the series and the value of m, meaning where the term ends. It's two different things, okay? But in some situations, it can be the same thing. And that is actually the situation. And this is why I'm saying so. Imagine that you had the sum of a series, but you were starting where n was equal to 0, for example. And let's say we were ending at 5. And if I asked you how many terms are there in this series, how many terms would you say there are? If you said 5, it's not 5. It's actually 6 terms, because you see that we have an n is equal to 0. So n is equal to 0, n is equal to 1, n is equal to 2, 3, 4, and then 5. How many terms is this? 1, 2, 3, 4, 5, 6 terms. Okay, so you need to be careful and check that this number is not 1 really. You need to check if it's 1 or not 1. Now, in the case that the number is 1, you don't have to worry, because the value of m, or where the series ends, would literally be the exact amount of terms that you have. And that is our situation. So k starts from 1, so I don't have to overthink it. Since it is sigma, we're speaking about the sum of series. So I'm going to say the sum of n terms of a what type of series? A geometric series, because that's what we're working with. And what's the formula for that? Well, remember there are two formulas. There's the one where r is greater than 1 and one where r is less than 1. Okay, so how do we find out what r is? Well, that's probably why they asked us to find the first two terms. We know it's geometric, we need to find r. Well, we can find r by saying term 2 divided by term 1. So I'm just going to say, I'm going to find r by saying 3 over 2 divided by 3. Okay. And you can use a calculator to do that, but I'm just going to say 3 over 2, and I'm going to change this. This is 3 over 1, and I change it to a multiply, and I swap the numerator and denominator. That's how to divide. It's really called tip and times. So we're going to have this. Those two will cancel, and you'll be left with half. Okay, even if you checked on your calculator, 3 over 2 divided by 3 is a half. So now that we have that, you see that this is a situation where r is less than 1. Okay, so I'm just going to use that. I'm going to use the one where r is less than 1, which looks like this. And surprisingly, it is what we just proved. Remember that we had to prove this. This is the situation where r is less than 1. Okay, so where r is greater than 1, then you would see that r to the power of n would come before the 1. They would just swap really. Okay, so that's what our formula is going to look like. So let me put that down. Okay, so we are saying the sum of how many terms? The sum of how many terms do we have? Well, remember how I said that here, because k is equal to 1, the number that you have here is literally the amount of terms that you have. So since we have m here, The amount of terms that we have, we would also call that m. Okay, but let me also give you a formula for this to find out how many terms there are in a series. When given the series in sigma notation, you need to do this. Okay, to find the amount of terms there are, you say the top number, that number there, minus the bottom number, that number there, and then you add 1. And you see, if we do that here, it's going to simplify to m still. So if you said m, the top number, minus the bottom number, which is 1, plus 1, you see that 1 and negative 1 cancel, and you're left with m. Okay, so that's what I'm saying. Sm is equal to, then we have a. What is the value of a? We know what the first term is. It's 3. So 3 multiplied by 1 minus r. Our ratio is a half. So I'm just saying 1 over 2 raised to the power of m. And I'm just going to call that m. And then close the bracket. Then we have 1 minus r. So that is 1 minus a half. Okay, now we also know what the sum of the series is. It's this number. So in place of Sm, I'm going to put that number down. So I'm going to say 3069 over 512 is equal to all of this again. But I'm also seeing that on the denominator, I can actually simplify that. So that's just 1 minus a half raised to the power of m all over 1 minus a half is a half. Okay, so that is simplified. Then what we can do next is, how about we just say 3 divided by a half and then put that number in front of the bracket. So we still have the 3069 over 512 is equal to 3 divided by a half would give you 6. Okay, because it's really just 10 times. Again, you could divide. And then we're going to have inside the bracket, we still have 1 minus a half raised to the power of m. Okay, so now we can get rid of the 6. So get rid of the 6 by dividing both hand sides by 6. And let's see what happens. So we're just going to have that one. I'll just use a calculator. So I'm just saying 3069 divided by 512, right? That is being divided by 6. And I'm going to leave it as a fraction. So we get 1023 over 1024. And this is equal to, and we're just going to have that cancel out. So you have 1 minus 1 over 2 to the power of m. Okay, and that bracket is gone now. Then what I'd rather do in this situation is I'd rather take this over, because it's negative. You see, negative then a half. And when you take it over, it becomes positive. So it's positive a half raised to the power of m. And now this is equal to, I still have the 1. And now I'm going to take this number over. And so that is minus 1023 over 1024. But then in this one, I can just see that I could have changed 1 to 1024 over 1024, really. And I'm saying minus 1023 over 1024, because when you subtract fractions, your denominators must be the same, right? So as you can see, 1024 minus 1023 is just going to be 1. So 1 over 1024. You can use a calculator. So this is 1 over 2 raised to the power of m. Okay, so now we are at the point where we have our exponential equation, and you can see we have bases and you have an exponent that is missing. At this point, you have to, in order to solve for the exponent, you need to try and make the bases the same. So how can this number be written as a base of 1 over 2? Well, the 1 is not a problem. The 1 is fine, right? It's the 2. So how can this number 1024 be written as a base of 2? Well, let's see how that's going to work. You can just say 1024 is equal to, then press shift and factorize, and it will factorize this for you. You see that 1024 is actually 2 raised to the power of 10. So this means that we have a half raised to the power of m, and it's equal to, now look at how I can write this. Because I know this is 1 over 1024, which I can write as 2 raised to the power of 10. If you said 1 raised to the power of 10, it's still going to be 1. So I didn't change its value, I'm just changing the way it looks. So this number, since they both have the same exponent, I can actually write them under a common exponent like that. So you see on your calculator, if you even say 1 over 2, and you raise all of that to the power of 1024. So then you just close that bracket. If you raise it all to the power of 10, that would give you 1 over 1024. Okay, so that's how you can change that. So as you can see, the bases are now the same. So that concludes that m is actually just equal to 10, because we can equate the exponents. So that's the value of m. Okay, and that is that question. Okay, finally moving on to the next question. Now, question 3.3, this is what we have. A ball is dropped from a height of 24 meters. Okay, so we have a ball being dropped from 24 meters. Every time the ball hits the ground, it rises 3 over 4 of its original height. So 3 over 4 of its original height, which of course is going to be this 24 meters. Okay, calculate the sum of the total vertical heights reached by the ball after the first bounce. So after the first bounce until it comes to rest. Okay, so let's understand this question. And I'm just going to use a drawing to really just break it down. So we have this ball, right? And this ball is being dropped from a height of 24 meters. Now, every time the ball hits the ground, so it eventually hits the ground, right? Every time it hits the ground, they say that it rises 3 over 4 of its original height. Okay, we have to really think about that. If it hits the ground, it rises 3 over 4 of whatever its original height was, which is the 24. Now, with the way this is being phrased, I don't think they meant of the original height. This is the reason I'm saying so. They said every time it hits the ground, it's going to rise 3 over 4 of its original height. If it did that, this is what's going to happen. It gets dropped 24 meters, it hits the ground, then it rises 3 over 4 of its original height. It hits the ground. Then it rises again 3 over 4 of its original height. Then it hits the ground. That's the reason why I'm saying I don't think they meant original height. I think this word should have been previous, because they say that it's going to keep doing this until it comes to rest. Well, if this ball is going to hit the ground and then rise 3 over 4 of its original height every single time, then this ball is never going to come to a rest. It's just going to keep reaching the exact same height, 3 over 4 of its original height, 3 over 4 of its original height every time. And that's not possible. So that's what I'm saying. I think this should be previous height, because it comes to rest at some point. So for it to come to rest, for it to eventually just stay on the ground, what it should be doing is it is reaching 3 over 4 of its previous height, meaning it gets dropped. This is the original height, right? Then it hits the ground and then it rises 3 over 4 of whatever the previous height was. Then it hits the ground again and then it's going to rise 3 over 4 of whatever the previous height is. This height is 3 over 4 times 24. So it's going to be 3 over 4 of this height now. This 3 over 4 times 24. And if I want to clean this up and just write it in the correct way, and let me just even show you, for example, the third bounce, right? The third bounce would be lower again. So it's going to hit the ground, then it will rise 3 over 4 of whatever this height was, not original, but the previous height. So it's going to be 3 over 4 of everything here again. Okay, so 3 over 4 of all of that. So if you clean this up, this is actually what this is saying. First, the ball drops from a height of 24, then it bounces and hits this. Now, because I can see that 3 over 4 is a ratio that keeps being multiplied here, this is how I can rewrite this. Instead of writing it like this, I can just say 24 multiplied by 3 over 4. So it's just multiplied by 3 over 4. Then this one, I can say 24 multiplied by, do you notice that there are two 3 over 4s? Brackets just mean to multiply. So just multiplying all these numbers throughout. So I could just say 3 over 4, because there's 2 of it, squared. Then the next one would have been 24 times 3 over 4 to the power of 3, and so on. Okay, but let's just make sure that we actually answering the question they're asking for. The question is, calculate the sum of the total vertical heights reached by the ball after the first bounce until it comes to rest. So after the first bounce. So think about it. This is not a bounce. This height of 24. This is just the height that the ball was dropped from. This is the first bounce. So this is where our pattern starts. Our pattern starts at this height, right? That 24 times 3 over 4. That's our first height. Height 1. And then this would be our second height that the ball reaches. This is the third height that the ball reaches. So clearly you see we have to start from here. That's the first term, not this 24, because they say after the first bounce. That is the sum of the total vertical heights we must calculate. So this clearly creates a series. And if you think about it, this series, we are only calculating the height that the ball reaches. But this series is going to converge. And this is why I'm saying it's going to converge. A series that converges, it really just means that the pattern is heading towards a specific number. And this is why I'm saying this. You see that the heights of these, they're getting smaller. Because 3 over 4 is a proper fraction. The numerator is smaller than the denominator. So every time you multiply this by 3 over 4, it gets smaller. So this is going to keep on getting smaller throughout. So it's going to keep getting smaller and then smaller and smaller and smaller. Now think about what's the smallest height, or what is the only height that this ball cannot reach, okay, or cannot go beyond. That height would be 0. Because when this ball reaches a height of 0, it's not even in the air anymore. It's now on the ground, okay? So the height that it will not go beyond, right, would be 0. So it's going to keep on bouncing. That's why when you watch a ball bounce, it just bounces, bounce. And you don't even know how many times it bounced until it stopped bouncing and it was just on the floor. So this is going to be, it's a geometric series. It's a geometric series that converges. These heights are heading towards a specific number. It's heading towards 0. Okay, so that's the sum of all the heights. So let's go ahead and write the pattern. The pattern is really the first term that we have is 24 times 3 over 4. Okay, that is our first height, because clearly they tell us the sum of the total vertical height reached after the first bounce. There's the first bounce, then it goes up. That's the first height, okay? So after the first bounce. Then, of course, the second one would be that 24 times 3 over 4 squared, then 24 times 3 over 4 to the power of 3. And this will keep going, and it's going to be heading towards 0. Getting closer and closer to 0. It will not go beyond 0. So, to calculate the sum of all these heights, because it's a converging geometric series, we have to use sum to infinity. And the sum to infinity formula is a over 1 minus r. And this is what we have. So sum to infinity, what is our a value? It's this, 24 times 3 over 4, and then over 1 minus, what's our ratio? So the ratio you can just find by saying this, term 2 divided by term 1. You see, if you say term 2 divided by term 1, look what's just going to happen. You're just going to have 24 cancel, and then 3 over 4 will also cancel. One of it cancels here, and that cancels. So do you see that the ratio is just 3 over 4? So 3 over 4. And then we can just put this onto a calculator and then get our answer. So let me go ahead and put it on. And our answer is 72. But remember, these are heights. So let's just go ahead and see exactly it's in meters, right? Because it was dropped from 24 meters. So the answer is 72 meters. And that is the answer for 3.3. And question 3 is a total of 14 marks. Okay, moving on to question 4. And now we're on question 4, and 4.1 says, use the diagram below to calculate, without the use of a calculator, the value of each of the following. Okay, so the first question is sine of negative theta. Okay, let's go ahead and simplify, or just fill in the diagram. So do you see that they gave you a point and they call that P, and the X value is -1 and the Y value is -√3. What you can first of all do is go ahead and draw a vertical line to the x-axis, and you know that it is perpendicular to the x-axis. Then we can go ahead and label our sides. So the first side that we have, you see that this is an x coordinate, right? It's -1. Where the x coordinate goes is over here, right? So it's saying that this is where -1 is. And then this is a y coordinate. So where the y coordinate goes is over here, because it's saying that this is a y value of -√3. Okay, so that's -√3. So the only thing missing right now is the radius, the hypotenuse. So we have to find that using Pythagoras. Since it is the hypotenuse, you find it by saying that r, we call it the radius. So I say r squared is equal to, and we're going to take the adjacent, so which is -1, all squared, plus the opposite side, -√3 all squared, right? So this is going to be r squared is equal to, that gives you 1 plus 3. 1 plus 3 is 4, so r squared is equal to 4. If you square root both sides, we don't have to say plus or minus, because a radius is always positive, distance is always positive. Even if you walk backwards, the distance is still positive. Okay, so r is equal to 2. So that is our answer. R is equal to 2 there. And the question that they want us to really just work on is 4.1.1. We need to find the value of sine of -theta. Okay, so you can use the diagram to do this, or you could just do this. Every time you see a negative angle, okay, when the angle is negative, you're going to add 360 degrees. So I see that theta represents an angle. It is negative, so I'm going to add 360 degrees to this. So it means that what I have right now is actually just sine 360 degrees and then my minus theta. Now do you see that this is actually a reduction? It's a trig reduction. This 360 minus theta appears in cos's quadrant. That's where we have 360 minus theta. So since this is saying sine 360 minus theta, sine is negative in this quadrant. So our answer is going to be negative sine, and we're reducing that angle, theta. So that's our answer, negative sine theta. Now using the diagram, what is sine theta? So we can just make that negative. Sine, remember in SOHCAHTOA, sine is opposite over hypotenuse. So the opposite side over the hypotenuse. That's -√3 over 2. So remember, we still have this negative here, and then the -√3 over 2. So our answer, when they multiply, is just going to be +√3 over 2. And that is the value of sine -theta. Okay, next question. And the next question, 4.1.2, we have to find the value of cos 2 theta. Okay, cos 2 theta, what does that remind you of? That is a double angle. So you're going to have to change it into one of the double angles that you know of. Now, I'm specifically going to change it into this because I know what sine theta is. That's why. So I'm going to change it into 1 minus 2 sine squared of theta. Okay, that's what it's equal to. And so this is just going to be equal to, we have 1 minus 2, and I know what sine theta is, so I'll just put that there. But I know it's squared, so whatever that answer is, it's supposed to be squared. So sine of theta is -√3 over 2. That was the sine theta, okay? And so it's -√3 over 2, and that's been squared. So you can put this on a calculator at this point, that's fine. But I'll just do it without a calculator. So 1 minus, and we have 2, and then this gets squared. If you get -√3 all squared, the root cancels and the negative also cancels because it's been squared. So it becomes just a 3, and then the 2 as a denominator also gets squared as well. 2 squared is 4, so over 4. So this is what we have. We have 1 minus 2 being multiplied. Remember, this is one term, two term. You always simplify it term by term. So this term must simplify together first. So 2 times this, this is what's going to happen. If you're saying 2 times 3 over 4, I can look diagonally and just cancel out what is common. I see that between 2 and 4, what's common is 2. So I can say 2 divided by 2 is 1 and 4 divided by 2 is 2. So that's what's left. So we have 1 times 3 over 2, which is just 3 over 2. So this we have minus 3 over 2. And then what is 1 minus 3 over 2? You can change 1 into 2 over 2. That is still 1. And if you're subtracting, you subtract the numerators, leave the denominator the same. So 2 minus 3 is negative 1 over, and then just 2. And that's your answer. Negative a half would be your answer. Okay, so that is it. I think for the trig diagram, that's it. Okay, and then we move on to 4.2. Okay, so we move on to 4.2, which says, without using a calculator, determine the value of the following expressions. So the first question, 4.2.1, says we have sine 75 degrees cos 45 minus sine 15 degrees and cos 45. Well, one thing about this, the structure we can see, it's probably a compound angle formula that we have to use here. Okay, so looking at this, how can we change this so that it can fit one of the compound angle formulas? Well, first of all, how about we change this, right? The sine 75 degrees. Let us use cofunctions and change it. So using cofunctions, I know that the cofunction of sine of 75 degrees would be cos of 15 degrees. Here's why. Okay, to change it, you just say sine 75 degrees, and you see 75 degrees is an angle that is less than 90 degrees. So it's really just that one that we have when you have sine of 90 degrees minus theta, right? Because it's an angle less than 90. If you have sine 90 minus theta, this becomes positive cos of theta. So what I'm saying here is sine of 90 degrees minus what gives me 75, because I'm trying to change the way this looks but not its value. So 90 minus what gives you 75? That's 90 minus 15 degrees, which makes sense now. Okay, 90 minus 15 degrees, and so this will change to cos of 15 degrees, and that's why I said the cofunction for sine of 75 degrees is cos 15 degrees. So I can change that to cos 15 degrees, and then I still have a cos here, and I'm just trying to follow one of the rules. I'm seeing cos, okay, and we've got 15 degrees, 45 degrees, 15 degrees, 45 degrees, which looks fine because I'm seeing that I can change it into cos's compound formula, which is cos A, cos B, right? And because I have a minus minus, sine A, sine B. So you see that you have cos A, that's 15 degrees, and cos B, that's 45 degrees. But I'm also seeing there sine A, I also have 15 degrees, and this is not sine, this is cos. But it's 45 degrees, and I needed to say sine of that second angle, which is 45 degrees. I needed to say sine of 45 degrees, but it's cos 45. But that's not a problem. This is the reason why, because you see cos of 45 degrees, we could use cofunctions here as well. The cofunction for cos 45 degrees is what? Think about it. It's going to be sine 45 degrees. So I can just say minus, I still have sine 15 degrees, and then sine 45 degrees, because that's the cofunction of that. And so that worked out perfectly like that. Okay, so you see that it is in the form of cos, sine, sine, and A, B. It is in that format. Okay, we have a 15, 45, cos, sine. Okay, so just like the way this simplifies to cos of A, and if you have a minus in the cos rule, you change it to a plus, right? In the cos rule of the compound formula. So we have plus the second angle, which is B. It's the same way we're going to simplify that one as well. Since there we have cos 15 degrees, we'll take cos, then 15 degrees is acting as our A, plus 45 degrees, because we have a minus, it changes to plus 45 degrees. And so this is equal to what is 15 plus 45? That's going to give you 60 degrees. So what's cos 60 degrees? You can use your calculator, but I would know that cos of 60 degrees has to be a half, because sine of 30 degrees is a half. And these are cofunctions, so they're equal to the same thing. So you can use your calculator. You can also use the triangles, special angle triangles. I don't really use the triangles. I use a rule called the OHA rule, which I'll probably just explain in another video. Okay, so the answer here is just a half. You can use a calculator and you will see that the answer is a half. Okay, so 4.2.2, this is what we have been given. And we have to simplify this, and this is for 6 marks. Okay, this is going to simplify to 3. Okay, that was easy. Very simple. 6 marks. And we're moving on to the next question. Lol, I'm just joking. Don't do that. You see what I just did there? That's what you're going to get if you take all of this and then just put it onto the calculator and get one answer. You will not get 6 marks. You will get 1 mark for your answer. That's all. So be careful not to do that. You actually need to do this instead. We have cos of 100 degrees divided by sine of negative 10 degrees times tan squared of 120 degrees. Okay, so how do we simplify this? Well, we can reduce cos of 100 degrees because it is an obtuse angle. It's not acute. But if you think about your cost diagram, right? Your reduction diagram. So we have CAST, cost. And then we have theta here. We have 180 minus theta. We have 180 plus theta and 360 minus theta. Where would 100 degrees fall, right? Okay, you can also include the angles, of course. So 0 degrees, 90 degrees, 180 degrees to 70 degrees, and then 360. So 100 degrees will fall in the second quadrant. So you're going to have to use the reduction of the second quadrant. So if I was reducing it, I would really just say cos of, I'm not going to write that down. I'm just going to write the simplified. So I would say cos of 180 degrees minus what gives me 100 degrees. It's going to be minus 80 degrees. You see, you're just changing the way it looks, not its value. So this is still represented as 100 degrees. Okay, so if you simplify that, that's just going to be, now remember that 180 minus theta is in sine's quadrant, meaning cos is negative. So if you reduce that, it's going to become a negative cos of whatever this angle is, because that's your theta. So negative cos of 80 degrees. So that's reduced, right? Okay, and then this goes, we're going to say over, and we have sine of negative 10 degrees. Okay, how do you simplify that? Sine negative 10 degrees, whenever your angle is negative, something you can do is add 360. There's 2 ways of doing this. Easy way and the more of a grade 11 method. So use the grade 11 method first. So if you have sine negative 10 degrees, just add 360 degrees to it. So 360 minus 10 is 350. But then you see this angle is too big and you have to reduce it. So if you reduce this, 350 degrees falls into which quadrant? Cos quadrant, okay, the 4th quadrant. So you'd have to use that reduction. Then you would say sine of 360 degrees minus what gives you 350 degrees, and that will be sine of 10 degrees. Okay, 360 minus 10 is 350. Then you see that sine, right? 360 minus theta, that's cos quadrant. So sine is negative in that quadrant. So sine, negative sine of 10 degrees. That will be your answer. Okay, that's actually what happens. Please don't get in the habit of saying, oh, I see negative here, I'm just going to push it there. It doesn't work for everything, okay? There's some functions that will not work for. For example, if you had cos of negative 10 degrees and you say this is equal to negative cos 10 degrees, that's not true, okay? That's why you need to understand why it simplifies to what it does and not just move things, okay? So that becomes negative sine 10 degrees. And that is really just the grade 11 method of working it out. In grade 12, really, a way that you can look at that is if you're looking at a Cartesian plane, negative 10 degrees, you're going to have to think about how it would be measured. If an angle is positive, you measure anti-clockwise. If it's negative, you measure clockwise. So negative 10 degrees would have been measured clockwise and would land in cos quadrant. So already it's in cos's quadrant and its reference angle is 10 degrees. Sine is negative in this quadrant. And that's how you know that your function will be negative and you'd still have 10 degrees. Okay, so that's another way of looking at that. But all in all, we know that this becomes negative sine of 10 degrees. Okay, so now that we have that, it's still being multiplied by all of this. Multiplied by tan squared of 120 degrees. Okay, I can reduce that. So tan squared of 120 degrees falls into which quadrant? This quadrant, because it is greater than 90 but less than 180. So you're going to have to use that reduction on it. 180 degrees minus what gives you 120? That would be minus 60 degrees. So if you reduce this, right, remember that the square is still there. It's better to actually write it like this. Tan then of 180 minus 60 degrees all squared. The reason I'm saying so is because when you simplify this, that can become positive or negative, depending on which quadrant it's in. But right now you see that this 180 minus 60 falls in the second quadrant. Tan is negative in this quadrant because only sine is positive here. So that tan becomes negative tan of your reference angle, which is 60 degrees, and then it's been squared. Okay, so I'm just simplifying it shorthand quickly. And now this is negative tan 60 degrees all squared. When you square a negative variable or number, it becomes positive. So this becomes positive tan squared of 60 degrees. Okay, and that's what we have there. And this is now equal to, now, how will this one simplify? Okay, so if you look at 80 degrees and 10 degrees, you see that these are cofunctions. You see how you know something is a cofunction? If you add the two angles, first of all, they need to be cos and sine. And if you're able to add both of them and they give you 90 degrees, those are cofunctions. So it means that we can actually change one of these. So you can choose any one, change any one, it's fine. It will still work out. So let's say we decided to change the sine, right? Let's change that. So what will sine of 10 degrees be? Okay, what is the cofunction of that? Negative, we still have on top negative cos of 80 degrees. And on the bottom, we still have negative, right? But we need to change sine of 10 degrees to a cofunction. So remember, since it's 10 degrees, it's an acute angle, right? You just have to find out what do you have to add to 10 degrees to get 90 degrees. And that would be 80 degrees. So it means the cofunction of sine of 10 degrees would be cos of 80 degrees because 80 plus 10 is 90. You can change it like this instead, where you just say, okay, fine, this is going to be sine of 90 degrees minus what gives me 10 degrees, and that's 80. Then you can change that now to cos of 80 degrees. That's another way of changing it. Okay, then since we have negative cos 80 over negative cos 80, you know they will simplify to 1. Here we still have tan squared of 60. So we can already just figure out what tan of 60 degrees is. You can use your special triangles. You can use other rules, or you can use the calculator. If I use the calculator, it's really just going to say tan 60, it's root 3, right? So it means that what we have is the square root of 3, but remember that this thing is squared, so all squared. And then here, these two simplify, they divide and give you 1, because it's the same thing divided by the same thing. Multiply by this squared. You see that the radical here will break, they will cancel because they're the inverse of each other. And that is just going to be a 3. So 1 times 3 is 3, and that's our answer. Okay, so this is what we have for 4.3. So we have to prove that for angles alpha and beta, that this is equal to this. Okay, so this is just an identity. So let's go ahead with the first one. Okay, so looking at the left and the right hand side, you see that which one can you actually work with things? Can you actually simplify here? The left hand side, okay? The right hand side is already, it's kind of simplified. It's not really much we can do here. So we can work on the left hand side. So I'll start off by saying the left hand side is equal to, and then I'll just rewrite whatever was on the left hand side. Okay, so this is going to be equal to, and we're going to have, first of all, we are subtracting. When you are adding or subtracting fractions, the denominators must be the same. So how do we make these denominators the same? Well, what we can do is, since the denominator here is sine beta and this one is cos beta, you can multiply this by cos beta over cos beta. Okay, numerator and denominator by the same thing. That way the denominator can be sine beta cos beta. And here we can multiply the denominator and numerator by sine beta. And then that way the denominators are the same. So this is what we'll have here so long. Sine alpha times cos beta is just going to be sine alpha cos beta over, we have sine beta cos beta minus, and here we have cos alpha sine beta over the same thing, sine beta cos beta, right? And now we can subtract. So we can finally say this is sine alpha cos beta minus cos alpha sine beta over their common denominator, which is sine beta cos beta. Okay, let's look at the numerator. Do you see that this looks like one of the compound angle formulas that we have? See, it's saying sine cos cos sine, right? It sounds like the compound angle formula for sine. And then you can see alpha, beta, alpha, beta. It is in the correct format. So this simplifies to, we can simplify it to sine of alpha. And we have a minus, but when it has to do with the sine, when it has to do with the sine formula using the compound angle formula, you don't change the sign. So that stays minus, and we have beta all over sine beta cos beta. And let's look at that right hand side. Does that look like it? No, not yet. Okay, so how do we get it to look like that? Well, I'm seeing that here we have sine beta cos beta, which looks very familiar. In fact, it looks like a double angle formula. Do you remember the double angle formula that we have that says if you have sine of 2, let's say beta, right? It's equal to 2 sine beta cos beta. Then if you made one of this the subject, if you made sine beta cos beta the subject, you would divide both sides by 2 to get rid of the 2. And then you would just have here your sine beta cos beta, and this would be equal to sine 2 beta over 2, which you can, if you like, call it like this is a 1 here, so it's 1 over 2 sine 2 beta. That 2 and that 2 cannot cancel. This is for the angle. Okay, this is the number. So it means you can change this into sine beta over, I would rather change it to over 2 really. Okay, instead of saying a half. It's not really necessary to say a half in this situation, but you can. It's still the same thing. So now you see that sine beta cos beta is actually equal to sine 2 beta over 2. So that's what we can change this part to. Okay, so on the numerator, we still have sine alpha minus beta. The denominator, we now have sine 2 beta over 2. You see, this numerator is being divided by this denominator. So how we could have written this is sine alpha minus beta divided by sine 2 beta over 2. Then because we are dividing, we're going to use the rule tip and times, meaning we tip the second fraction that we have. This fraction, you swap the numerator and denominator. So now 2 over sine 2 beta. And then you change the division sign into a multiplication sign. And then, of course, we'll still have the first fraction being exactly the same. So we still have here sine alpha minus beta. Okay, so now that we have this, we can just simplify. And we can just say this is finally equal to, if you say this, remember this is as a fraction, it's really just sitting over 1. That's how it is. So numerator times numerator, this times this just gives you 2 sine alpha minus beta over 1 times sine 2 beta is just going to give you sine 2 beta. And that's your answer. Okay, this was just showing you how to get that. Okay, so now if you compare this to what we have here, you see that it's exactly the same. So this really is equal to the right hand side, and the identity has been proven. Okay, moving on to the next question, which was really just a continuation of this. It was a hence question. Okay, moving on to the next question. Okay, so now we're on 4.3.2, and 4.3.2 says, hence or otherwise show that sine 5 beta over sine beta minus cos 5 beta over cos beta is equal to 4 cos 2 beta. Okay, so very big emphasis on the word hence. They say hence, meaning whatever we're going to do now has a lot to do with what we previously did. If you look at the structure of the way this looks, it looks a lot like the previous expression, the previous identity, really. So you see that we have sine alpha over sine beta as well, and then minus cos alpha over cos beta. But look at what we have here, sine 5 beta. So the only difference is this, right? Sine 5 beta still over sine beta, and then cos 5 beta over cos beta is exactly the same. Okay, so let me just bring down that expression down here so that we can just compare it. So if you look at these two, they look very similar. You see that here we have an alpha, and then here we have an alpha. But here we have 5 beta and 5 beta. So since we already know that this expression simplified to this, why don't we use the same method, right? Why don't we also simplify this expression using the rule that we used here? If we were able to simplify all of this so that it can become 2 sine of alpha, right? There's our alpha, minus beta over sine 2 beta. Then it means that we can do this to this one. So we're working with the left-hand side. So of course, I will say LHS is equal to, and then rewrite what we have. And then simplifying this expression using the rules that we have here. Here we had alpha and alpha, but here we have 5 beta and 5 beta. So we're going to rewrite exactly what we have here, but where we see alpha, we're going to replace that with 5 beta. Okay, since everything is exactly the same and it did simplify to that. So this is what we can say. This simplifies to 2 sine, and there I see alpha. So I'm going to change that alpha, it was alpha here, to 5 beta instead. So 5 beta, and then minus beta, because we still also have beta here, minus beta, all over sine 2 beta. There's also sine 2 beta. So you don't have to go do all of that from overs again. No, we already knew how to simplify this one. So we're just using whatever rule we used here to simplify this. Okay, so now looking at this, look at what we have. You see 5 beta minus beta, those are like terms. So we have 2 sine 5 beta minus beta is 4 beta over sine 2 beta. Okay, we need to get it to look like this. So since it needs to look like that, you see that there's a cos and there's a 2 beta. There isn't a 4 beta though. So it means that this 4 beta has to leave. Okay, so how can we actually get that to simplify to something else? Well, this is a double angle. So do you remember the double angle formula that says that sine of 2a, so sine of a double angle, so sine of a double angle is equal to 2 sine of a, half of that angle, right? Cos of a, also half of that angle. So it means if you have this, remember we still have the 2 outside, but then this means the sine of 4b, that can actually change into 2, so I'm just saying multiply by 2, right? Sine of half of this angle, since this angle is 4b, half of the angle would be 2b or beta, and then cos 2 beta. Okay, so that's double angle being used on that. Then we say over sine 2 beta. So over sine 2 beta. Now do you see that sine 2 beta and sine 2 beta can cancel? Then on top you just still have 2 multiplied by 2 is 4, and you have cos 2 beta. And that is how we get to that. So it's finally equal to our right hand side. So that's equal to the right hand side. Okay, so that is that question. And then moving on to the next question. Okay, question 4.4 says, determine the general solution of this expression. So find the general solution of 2 sine squared of x minus sine x minus 1 is equal to 0. So I want you to look at that expression and ask yourself, what does it remind me of? Okay, it actually is a trinomial. So let's imagine, right, that let's say sine of x was k. Let's replace sine of x with k. So if we have that, that's going to be 2k squared, because that's sine squared of x, minus k minus 1 is equal to 0. So factorize this. If you factorize this, you can use the cross method. You can also use the factor method. So I'm just going to use the factor method because I have used the cross method multiple times in my video. So let me just try a new method. Okay, so factorizing using the factor method where we look for factors. What we're going to do first of all is we are going to take the coefficient of k squared and the constant term, and we're going to multiply it. So 2 times negative 1 is negative 2, right? Then we're going to think about factors of negative 2 that can give us a negative 1 in the middle, like we have the coefficient of k. Okay, so let's think about those factors. The factors of negative 2 would just be 2 and 1, but one of it has to be negative. So which one should be negative so that you can get a coefficient of negative 1 in the middle? The 2 should be negative, and then the 1 should be positive. So now that we have that, look at how we can write this. This is now 2k squared, and we're going to write these numbers, but they're going to have variables of k with them. So it's going to be minus 2k, and then plus 1, which we can also just call plus k, and then minus 1. We continue there. So in other words, what we just did here is we took this negative k and we broke it up into negative 2k plus k, which if you add, you still get negative k. Okay, now that we have this, we're going to work with grouping. So we're really just grouping the first 2 together and those last 2 together, okay? And what we're going to do here is we're going to take out the common factor that you see in each group. In this first group, the common factor is 2k. Then open a bracket. What is left after you take out 2k in 2k squared? You just have a k. You can also say 2k squared divided by 2k. And then here, what you have left, if you say negative 2k divided by 2k, you get negative 1. Okay, now look at the second group. What can you take out as a common factor? It looks like nothing is common, but it's actually 1 that is common. We can take out positive 1 as a common factor. And then open a bracket, and we're just saying k divided by 1 is still k. Negative 1 divided by 1 is still negative 1. And you see now that you have the same bracket, a common bracket. So this is grouping that we're using. And so now that we have a common bracket, we're taking out that common bracket as a common factor. And then opening a bracket and writing what is left. What is left? In the first term, this term, we have 2k being left. And in the second term, we have positive 1 being left. And that is going to be our answer. And of course that they're all equal to 0 because it is an equation, right? Then you could solve for k. You can say finally means that k is equal to, it's taking that negative 1 over positive 1. Or you can say 2k is equal to, and I'm also taking that over, it becomes a negative 1. Then we can divide both sides by 2 just to simplify. And then after that, k is equal to negative a half. But remember, we're not trying to solve for k. We're trying to solve for the general solution of this. Okay, then if you simplify this, I'm just using the k method. I didn't have to. I could have just simplified it by factorizing this, but just to make it simpler. So remember that we let sine of x be equal to k. So in place of k, just put sine of x back. It means that what we're actually saying is that sine of x is either equal to 1 or sine of x is equal to negative a half. Okay, that's another way that you can solve for that. That's, of course, if you found the whole signs being intimidating, then you could have done that. Okay, so now that we have this, we just have to find the general solution. Okay, so finding the general solution of this, you can draw a cost diagram just so that you know what to do here with this. Okay, so the first one we have sine. So sine of x is equal to 1. And I'm just going to be using really the standard method that we use throughout, like even in textbooks. There are other methods which I will discuss more in the future. But for now, let's just stick to this, using this. So since we have sine of x being equal to 1, first notice that 1 is a positive number. So really what we're saying is that sine is positive. So let's think about the quadrant where sine is positive. Sine is positive in the first and the second quadrant. So we will use those reductions. So this is what's going to happen. Now we need to find our reference angle. To find the reference angle, you see, we're just saying our reference angle is found by taking sine over. So it's really the second function of sine. So if we take sine over, we get the second function of sine, which we activate on the calculator by saying shift sine, and then we're saying shift sine of 1. That's the number that we have there. So it's really this. So just saying this of 1. Okay, so that gives us 90 degrees. So the reference angle that we have is 90 degrees. Okay, so since we have 90 degrees, we're looking at this, right? In the first quadrant, all we have is theta. Theta is going to represent your reference angle. So since we just have theta, our answer for x is either equal to our reference angle, theta, which is just 90 degrees. And then because this is sine, okay, the sine graph repeats itself every 360 degrees. So you need to say plus k of 360 degrees, okay? We will say where k is an element of integers, of course. Then you can, if you wanted to, also find out this part, but you see, this is the reason I wouldn't do that. Because you see, if I said, oh, x is equal to, then I also said, okay, 180 degrees minus, since, you know, it happens in these two quadrants, minus 90 degrees, then you see 180 minus 90 is also 90. So you don't have to include that. For a number like 1 and negative 1, you don't really have to include two quadrants. It's going to be the same number at the end of the day. Okay, so that's the solution for sine of x being equal to 1. That's the general solution where sine of x is equal to 1. And then in this part here, where sine of x is equal to negative a half. Okay, so how do we find that? Well, again, let's look at the fact that you have negative a half. So in other words, they're telling you that sine is negative in this quadrant. So where is sine negative? Sine is negative in tan and cos's quadrant. So we will use those reductions. Okay, so our next solutions are these ones. I'm saying I'm going to first of all get the reference angle. Again, it's by taking sine over. And then in this one, look at how this is done. Yes, we'll take sine over and get the second function, but you're not going to take negative a half. You just take the absolute value. You take a half. Okay, regardless of whether it is positive or negative, just take the number there. So if you say shift sine of a half in your calculator, you'll notice that you will get 30 degrees because sine of a half is 30. So shift sine of a half, that's 30 degrees, right? So that is our reference angle. Then we're going to say x is equal to, I can still leave that all there, okay, because they're all just solutions for x. X is equal to, and look at the reduction we have here. Remember how I said theta is basically your reference angle, okay? That's really what it is. So we're saying 180 degrees plus theta, meaning 30 degrees. Then you still have to say how many times it's going to repeat because it's a general solution. It's not a specific solution. So we're saying plus k of 360 degrees again, or x is equal to, and we're saying 360 degrees minus theta, which is 30 degrees, and again plus k of 360 degrees. Make sure you tell them that k is an element of integers. You just have to say it once so they know what k is. Okay, so x is finally equal to 180 plus 30, that is 210 degrees, plus k 360 degrees, or we also have 360 minus 30, which of course is going to give us 330 degrees plus k of 360 degrees. So these are our solutions. That's our first solution, second and third solution for these two equations that we had. Okay, so that is how you can do that. Remember, you don't really have to use that k. You just use the k if it looks intimidating, but otherwise you can just simplify it like you normally would when you get your factors. You could have written that as 2 sine x plus 1. Okay, and sine x minus 1 is equal to 0. Then go ahead and solve for x. Okay, but that is the end of question 4. And question 4 is 30 marks in total. We finally move on to question 5. Okay, so now we're on question 5, and question 5 says, in the diagram below, M is the center of the circle, DABC. Then we have EDF is a tangent to the circle at D, and FBG is another tangent to the circle at B. So we have 2 tangents to this circle. Okay, and as you can see, we have an angle 140 degrees, and we have that being 28 degrees. Okay, so the first question is calculate the following angles with reasons. So you need to find the angle C. Okay, that doesn't look so bad because you see where C is. You always have to ask yourself, where is this angle? And then what kind of theorems can I use because this angle is where it is? This is at the circumference. So think about theorems with angles at the circumference. I see that we have 40 degrees here, and right opposite that we have that. So remember that in a cyclic quad, the opposite angles are supplementary. They add up to 180 degrees. So if this is 140 degrees, then it means that this is 40 degrees. Okay, so we're just going to say angle C, you don't have the right calculations, not really necessary. Angle C is equal to 40 degrees, and you just put your reason because opposite angles in a cyclic quad are supplementary or add up to 180 degrees. Okay, so there is that reason. Moving on to the next question. Make sure to be filling in the numbers. They will really help you a lot as you go along the questions. Okay, the next angle they want us to find is angle M1. Angle M1, okay, look where angle M1 is. It is at the center. What are the rules that we know, theorems that we know about angles at the center? The angle at the center is twice the size of the angle at the circumference as long as it's supported by the same chord or arc. Do you see that that angle C is supported by this chord DB, and angle M1 is also supported by DB. So it means the angle at the center is twice the size of this angle at the circumference. So it means the angle at the center is 80 degrees. Okay, so again, angle M2 is equal to 80 degrees because of angle at the center being twice the angle at the circumference. Okay, then moving on to the next question. Okay, so 5.3, we have to find angle B3, which is a common question, really. Looking at where B3 is. Do you see where B3 is? Okay, so let's understand something quickly. They told us that M is the center of the circle. So if M is the center of this circle, then it means that MB is a radius and MD is also a radius, which would mean that they are the exact same length. So we can start off by telling them that. We can tell them that MB is equal to MD because they are radii. You don't even need to say equal radii. You can just say radii. Okay. Now that we know that they're exactly equal, what would that make this triangle? Or what type of triangle? It will make it an isosceles triangle. And because it's an isosceles triangle, it means two sides. If two sides are equal, then two angles are also equal. So this and that are exactly the same, right? So I'm going to state that those two angles are equal. Angle B3 is equal to angle D3. So angle B3 is equal to angle D3. And the reason it's not necessarily isosceles triangle, it's because the angles opposite equal sides are always equal in a triangle. Okay, so now that we have that down, look at what we can do. Okay, so we know these two angles are equal in this triangle. And in this triangle, we also have the angle M1, which is 80 degrees. Now we can use the sum of interior angles in the triangle. We can tell them that angle M1 plus angle B3 plus angle D3 should all be equal to 180 degrees. But for M1, I'm just going to say 80 degrees because I know its size already. So plus angle B3 plus angle D3, right? But the thing about this is they want us to find the length of angle B3. And we know that B3 is equal to D3. So in this equation I'm about to write, why don't I just replace D3 with B3 so that we can make B3 the subject of the formula? of the equation really. And so we have angle B3 there, right? And now that we have that, it's equal to 180 degrees. And this is because of the sum of angles in a triangle, okay, that they equal 180 degrees. And now that we have this, look at what we can say here. You see, if you say B3 plus B3, that gives you 2 angle B3, which is equal to, we have 180 degrees, and then we can go ahead and take this 80 degrees over, which becomes a negative 80 degrees. And so we have 2 angle B3 is equal to 100 degrees. Then we can divide both sides by 2, and that means that angle B3 is equal to 50 degrees. So that's a way that you can do that in a neat way so that it's just done one time. Okay, and that is for 3 marks. Okay, moving on to the next question. Also, before I forget, make sure to just write down everything you have. This is 50 degrees, and likewise this is also 50 degrees because those two angles are equal. Okay, the last question, 5.4, says angle D5. So we need to find angle D5. Okay, so where is angle D5? Here. And it's by the tangent. So remember, you can use tan chord theorem where you see a tangent. So we have a tangent and angle D5 is over there. Remember that the angle between the tangent and the chord, which is angle D5, is always going to be equal to the angle in the circle, okay, at the circumference that is supported by the same chord DC. So which angle in the circle, okay, that is at the circumference is supported by DC? That would be this angle, this full angle of angle, not really angle B, I would just say this angle B3 and this 28 degrees. So you see that those two would be equal. Angle D5 is actually equal to this plus this. Okay, so that's what we're going to do. Angle D5 is equal to 50 degrees plus 28 degrees, and because of the tan chord theorem. So angle D5 is finally equal to 130 degrees. Okay, so that is the end of that part, question 5. We still move on to more Euclid in question 6. Okay, so question 6, this is what we have. In the diagram below, NP and NM are tangents to the circle. So that is this and that. Then they tell us at P and M, right? K is a point on the circle. K is a point on the circle. KP, KM, and PM are chords so that angle K is equal to X. So that they've already made an X somewhere. Okay. Then they also tell us that L is a point on KM so that KP is parallel to LN. So these two lines are parallel, right? That we have. Then lastly, L and P are joined. Okay. So the first question is you need to prove that NMLP is a cyclic quadrilateral. So this is this quadrilateral that we have over here. We have to prove that that's a cyclic quadrilateral. When you have to prove that something is a cyclic quadrilateral, there are actually 3 ways. And let me actually list them down so that you can see why I'm going to choose the specific way to prove that that is a cyclic quad. There are 3 ways to prove something is a cyclic quad. The first way is, they all have to do with theorem really. First theorem you can think about to prove something is a cyclic quad is if you have a quad and the exterior angle of that quad is equal to the opposite interior angle, then the shape is a cyclic quad. The second scenario for you to be able to prove that something is a cyclic quad is, again, if you have a quadrilateral inside a circle. It's not a cyclic quad yet, it's just a quad. And you see that the opposite angles add up to 180 degrees, right? When you add them, they give you 180 degrees. Then this is a cyclic quad. And then the third way to prove that something is a cyclic quad is if you have a quad and you notice that you have lines like this, right? Just going across like that. And you notice that this angle is equal to this angle. Then this is a cyclic quad. So this is angles in the same segment. You see the 3 theorems that you can use to prove that something is a cyclic quadrilateral. These are the 3 ones. Now, out of these 3, look at this diagram, right? NP, LM. Look at that shape. Which one do you think would be best based on the way the shape looks to use? It would be this one. I would use this one because of the way the fact that I can see lines crossing like that. Do you see? That's a line doing that. So you can use that instead. I'm not even going to think about these. I mean, you can, but I'll immediately jump to let me try and use this because of the shape. Okay, so let's go ahead and see how does that work. Okay, so in other words, I either have to prove that this is equal to this, or of course I can prove that this is equal to this, or the other way around is why I can prove that angle P is equal to that, or I could also just prove that those other two are equal, these two, this and that. Okay, but let's just see. I'll just start with the basic one. So let's try and see if angle N2 is actually equal to angle P2. How can this happen? So I looked at that for a while, and maybe there is a way to prove it, but I'm not really seeing it now. So I've decided to try this because I'm actually seeing a way that we can actually prove this, that angle M is equal to angle L2. If we can prove those two are equal, then this shape is a cyclic quad. So how can they actually be equal? Let's look at that. Do you remember that NM, right, is a tangent? And you know that the angle between a tangent and a chord is always going to be equal to the angle supported by that same chord. So angle M1 should be equal to angle K, which is X, because it's the angle between a tangent and a chord, and this chord is supporting this angle. Okay, so I can already immediately tell them angle M1 is equal to X because of the tan chord theorem. Okay, so now that I know M1 is X, by M1 I'm just going to say X. Okay, the next thing I need to try to find is this angle L2. I need to find L2 so that I can actually show them that yes, those two are equal. So let's see L2. How can we actually find L2? But now as I look at it further, I'm seeing that these two will not work together. However, finding this is actually still going to help. The two angles that we can use that are going to be equal to each other is actually angle P1 and angle L1. Because if you look at it, you see that we can actually find angle P1. Remember, this is a triangle. If this is a tangent and this is a tangent, then tangents drawn from the same point to a circle are always going to be equal. So we have an isosceles triangle. So I'm already going to mention that NM is equal to NP because of tangents drawn from the same point to a circle are equal. Okay, so now that I have that down, that would mean that angle M1 is equal to angle P1. So this is also X. Okay, and that's because angles opposite equal sides are equal. Okay, so now that we have that down, and I've called that X, then look at what we can do here. Remember that we have parallel lines, right? This and this, those two are parallel. So we can have fun angles here. So if you try to look for alternate angles, sure, you'll find it, but it's not really helpful with what we want to do here. These alternate angles, they're not really helpful because I don't know what P3 is yet. But if you look at corresponding angles like that, right? So this angle and this angle, they would be equal. So it means that angle K or X is equal to angle L1. Okay, so I'm going to put that down. So angle L1 is equal to angle K. Angle L1 is equal to angle K. So it's also equal to X. And that's of course because of corresponding angles. That's fun angles that we have there. Okay, because corresponding angles on parallel lines are equal. And I just specify the angles that we're speaking about, the lines I mean. Okay, so we also know that that is also X. So I can just put that down. If this one is also X, now do you see what we have? We have the butterfly theorem or the bow tie theorem, which is angles in the same segments are equal. This is one of the requirements to prove something is a cyclic quad. So you can conclude, therefore it means that angle M1 is actually equal to angle L2. So that's what I'm concluding first, that angle M1 is equal to angle L2. And so since they're equal, it means that that shape is actually a cyclic quadrilateral. NMLP is a cyclic quadrilateral. And then of course, I'll give that theorem's reason. And the reason is because angles in the same segment are equal. You can also say angles at the circumference supported by the same chords are equal. Okay, so there We have proven that that shape is a cyclic quadrilateral, and that is for 4 marks. Okay, moving on to the next question. Okay, so the last question in question 6.2 says, prove that triangle KLP is isosceles. So we have to prove that that is an isosceles triangle. Okay, let's look at KLP. So this is KLP. How do we prove that that is an isosceles triangle? Okay, so if it's an isosceles triangle, two sides must be equal, right? Because, and the only reason I'm saying this is because we don't actually have physical lengths. Like, I don't know, this is 5 centimeters, for example, right? But we do have the angles. We have them in terms of x. If we can prove that in this triangle, two angles are equal, then it will also mean it's isosceles as well. Okay, then it will also mean that two sides are equal. And so therefore, it's an isosceles triangle. Okay, so in order to prove that this is an isosceles triangle, let's think about what should be equal. Since we have x here, right? For example, if this was also x, then the two angles equal in the triangle, it's isosceles. If this was also x, then two angles are equal, it's isosceles. Okay, so if we can prove that these two are equal, or prove at least that these two are equal, or these two are equal, then this is an isosceles triangle. So let's look at the triangle and let's attempt to find one of the angles in this triangle. That's really the only thing we have to do. We have to find one of the angles in the triangle, and then we'll be able to see if it's isosceles or not. Okay, so since K is already found, we need to either find P3 or L3. Okay, let's say we were trying to find P3, for example. What are the rules that we can use to find that? And looking at that, immediately I already see something that we can use here. Do you remember that these two lines are parallel, right? PK and NL. If you want to find angle P3, then do you see that when you draw the transversal, then it means that angle P3, right, because we have alternate angles, would be equal to angle L2. So there. Okay, that actually worked out just fine immediately. So since L2 is equal to P3, I can just state that. So I can tell them that angle P3 is equal to angle L2, which is of course also equal to x. And this is because of alternate angles on parallel lines, of course, and I'll specify the parallel lines. Okay, so now that we have that, I know now that that one is x. And here, look at what we have. We know that this is x. And this is also x. So you have two angles in the triangle being equal. It means that this is an isosceles triangle. Okay, so because we have the two angles being equal, we can actually tell them which sides are equal, because an isosceles triangle is a triangle that has only two sides equal in that triangle. So this would mean that since we have this being x, the side that should be equal is the side right opposite this angle, which is the side LK. That LK should be equal to the side opposite the second equal angle, which is this side PL. So it means that PL and LK are equal. So I'm going to state that down first. Tell them that PL is equal to LK, right? Because now that we know that the angles are equal. Okay, so now that we have this, my reason for this is really, remember the other reason when you have a triangle and two sides are equal, to find out, let's say if this is x, to find out what this is, you would say these two angles are equal because of angles opposite equal sides, right, are equal. But in this situation, what we had was that we have two angles that were equal. And so now we're concluding that the two sides are equal. So I can say sides opposite equal angles are equal. That's my reason here. Okay, so it's really just the opposite of the other one. Okay, so now that we have two sides being equal, it means that this triangle is isosceles. So we can just conclude, say, therefore, it means that triangle KLP is isosceles. And our reason is because two sides in the triangle are equal. Okay, and that is it for question 6. And question 6 is a total of 10 marks. And we move on to question 7. Okay, so now we're on question 7. And question 7 is a proof. And this is actually a proof that I have on my channel. But for the sake of this past paper, I will include it. Okay. So what we are told is that triangle PQR, this bigger triangle, and triangle FGH, the smaller one, are given. And then they tell us that angle P is equal to angle F, and angle Q is equal to angle G, and angle R is equal to angle H. And what we have to do is prove the theorem, which states that if triangle PQR and FGH are equiangular, then it means that PQ over FG should be equal to PR over FH. Okay, so in order to prove this theorem, the first thing that we're going to do is we're going to draw points on this big triangle. You need to make sure you always show them whatever you're constructing. So we're going to construct points, and let's just call this points A and B. So we're going to draw a point on PQ, and we're going to call that point A, right? And let me just actually make it look more logical and call that point A, right? And we're going to construct that point A. We're going to put it in such a way that PA is exactly equal to FG, right? So I'm saying it, and I'm also just going to write down any constructions that I'm making. So that is the first construction. We're just going to draw point A on PQ in such a way that PA is actually equal to FG. Okay, then we're going to do the same for this line PR. We're going to draw another point, and let's call that point B. Going to draw point B on PR in such a way that PB is equal to FH. Remember, these two are not equal, but this is equal to this. Okay, so I'm also just going to write down that construction. Right, okay, so now that that is down, then the second thing we're going to do is we're going to join A and B to form a line. Okay, you can use dotted lines instead. Okay, so now we're done with the construction. We can get into proving. The next thing we're going to do is we're going to look at these two triangles, and we are going to focus on this triangle, PAB, and this other triangle, FGH. And why we're focusing on them is because we actually want to make this line AB, right? We need to prove that it's actually parallel to the line QR. That's the only way. Then using, of course, the proportionality theorem, we'll be able to take sides over each other, okay? So we just need to make these two lines parallel. We need to prove that they are parallel. So what we're going to first of all do is prove that these two triangles are actually congruent, okay? So to prove triangles are congruent or similar, you first have to introduce the triangles. So I'm saying in triangle PAB and triangle FGH. So I need to introduce the triangles. So say in triangle PAB and triangle FGH. Okay, and now we're going to see the things in these two triangles that are equal. First of all, you see that angle P is equal to angle F. They already told us that in the beginning. That was given. So we can just say that is given. So angle P is equal to angle F. That is a given angle, given equal angle. And then the next thing that we see are equal is that PA is equal to FG, because we made it equal. Okay, we put it in such a way that it was equal. So that's really just by construction. So PA is equal to FG. So I'm going to remember that it is an equal side and it's equal by construction, right? By construction. And then the second side that is equal in these two triangles would be PB and FH. So those two are also equal. So I say PB is equal to FH. And it's a side that is equal also by construction. So the only reason I'm writing side is so I don't forget what was equal. Was it an angle? Was it a side? Now that we have this, we can finally conclude that it means that triangle PAB is actually congruent to triangle FGH. Okay, so they're congruent because, as you can see, you have an angle, a side, and a side being equal. So I can say angle, side, and side. Okay, so now that we have that, for angle, I can actually just use or you could say A is still fine. So do you see now that we have those three things being equal? And so it means that these two triangles are congruent. When two triangles are congruent, it means all their corresponding sides and angles are equal. Meaning, now this means that you see this angle A, it will also be equal to angle G. And angle B, it will also be equal to angle H. And I'm going to put that down because that is a very important part of proving that these two lines are parallel. Okay, so angle A is equal to angle, therefore it means that angle A is equal to angle G, and it means that angle B is equal to angle H. Okay, because they're congruent. So you can say because of congruent triangles that we have. Okay, so now that we have that because of congruent triangles, what else did we know was equal? Do you remember that angle Q initially was already equal to angle G, right? So think about it. If angle A is now equal to angle Q, but angle Q is equal to angle G, that means that angle Q and angle A are equal, okay? So this is what I'm going to say here. I'll tell them, but I knew that angle G, right? Angle Q, sorry, was equal to angle G, right? So first of all, tell them, but angle Q is equal to angle G. And I also mentioned the other one. It's not really necessary. You can focus on just one. So an angle R is equal to angle H, right? So an angle R is equal to angle H. We don't actually have to focus on both of them. One angle just has to be equal like that. Okay, so I'm not really going to focus too much on that. I know that angle Q is equal to angle G. So this now concludes that these two angles are equal. Angle A is actually equal to angle Q. Okay, since they're both equal to the same angle. So it concludes that angle A is equal to angle Q. Okay, so I'm saying that those two are equal. Okay, so now let's look at where we're going with saying that angle A is equal to angle Q. This is actually the whole point of this. Because angle A and angle Q are equal, right? Think about fun angles and the type of shape that this forms, the type of letter that it forms. If you draw that, right, with the angles, do you see that this draws an upside down F? So it means that we have corresponding angles. You have two angles that are equal, they're corresponding angles. Corresponding angles can only be equal on parallel lines. Okay, so we can tell them that since angle A and angle Q are equal, of course, this little part of angle A. I should have actually been specific about that. Instead of calling it A, I'm going to call it PAB because there's also this part, you see. So let me actually just call that PAB, right? Because those two angles are equal, it means that AB is parallel to QR because of corresponding angles, okay? So therefore, AB is parallel to QR, and our reason for that is because of corresponding angles. Corresponding angles are equal, okay? So therefore, the lines are parallel. Okay, so now that we have made these two lines to be parallel, this is the whole point of this. Now we can use the proportionality theorem. You see, the proportionality theorem states that if you have a triangle and you have a line being drawn parallel to one side of the triangle, then this is what we can say. Now, I'm going to try my best to just keep it within what they're speaking about here. They specifically said, you see, we have to prove that PQ over FG. Now, I have to take the side in this triangle PAB that is equal to FG, which is the side PA. So when I'm using the proportionality theorem here, I'm going to say that PQ over PA is equal to PR over PB, okay? And then you can just say line drawn parallel to one side of the triangle. That's your reason, okay? Or line parallel to side of triangle. Now that I have that, now that I have this down, you're going to have to focus on the fact that we said PQ over PA, but we already know that PA is equal to FG. We also know that PB is equal to FH. So I'm going to state that down, which I don't actually have to say this, but I just want to put it in as a conversation really that we're having. So I'm saying that PA, I know that I already proved that PA is equal to FG, and I also know that PB is equal to FH, right? So if those are equal, because I know this is equal to this and that is equal to that, then this is what it concludes. Now I'm still going to use this, but I'm going to replace where I see PA, I'll put FG. Where I see PB, I will put FH. So this concludes that PQ over FG is equal to PR over FH. And that's how we prove exactly what they told us to prove, as you can see there. And that's how we prove that equiangular triangles, okay, would have their proportions put over each other being equal. Okay, so that's how that works out. It's also on my channel as a proof. And moving on to the next question, this was question 7, moving on to question 8. So now we're on question 8, and question 8 says, in the diagram below, TP is a diameter in the circle with center O. TP is extended to R. Then they tell us that RM is a tangent to the circle at N. So here's RN being RM, really. Okay, that whole thing is a tangent. And then MO intersects chord NT at W. And we are told that NP is parallel to MO. So that's another important thing to look at. And lastly, WTO, that angle is 30 degrees. Okay, so the first question is, give with reasons 3 other angles equal to 30 degrees. So here is 30 degrees. Let's see 3 other angles that would be equal to it. So we just have to look at, there's possibly angles that are directly equal to this. Okay, so this is at the circumference. So angle at the circumference. So let's think about that. I see we have an angle at the center, but that's not really helpful. Okay, supported by the same chord. However, what I am seeing now is, do you see that this is at the circumference? Thinking about theorems with angles at the circumference. When you think about the tan chord theorem, it's also speaking about an angle at the circumference, because it says the angle between the tangent and the chord is equal to the angle supported by that same chord, you see? And that angle, right, supported by the chord has to be at the circumference. So that's the first one. So you can see that angle N4, because of the tan chord theorem, should be equal to angle T. That's 30 degrees. Okay, so I'm already going to put down that is also 30 degrees. So let me put it in blue. So that's 30 degrees as well. And I'll show them that angle N4, that's the first one. Angle N4 is equal to angle WTO, which they called it, which is equal to 30 degrees. And it's because of the tan chord theorem. So that's the first one that we have. Okay, it's for 3 marks because you really get a joint mark with your statement and reason. Okay, so that's the first one. We know angle N4 now, what it's equal to. What else do we have? Okay, since we have, I'm also looking at the fact that this angle 30 degrees, right? It is created because of this line, of course, but also because of this line from the center to the circumference. So if you have a line from the center to the circumference, that's a radius. And look for another radius that helps to form a triangle with this angle. Okay, so if you look at that, from the center to the circumference is ON, and then this is our triangle. So it means that if you have a line from the center to the circumference, it is a radius, so it's going to be equal to this other radius ON. So first, let's go ahead and state that those are equal. So I'm going to just tell them that OT is equal to ON because they are equal radii. And now that they are equal, I can tell them that these angles opposite equal sides are also equal because it's an isosceles triangle that we have here. So that is also 30 degrees. So angle N2 is equal to 30 degrees. Okay, equal to WTO, which is 30 degrees. And the reason is angles opposite equal sides are equal. Okay, so that's the second angle that we have that is equal. And now we need to think about a third angle. So you have to keep looking at maybe this one is equal to another angle somewhere, or maybe even this one is equal to another angle somewhere. Another thing that you can keep doing is go back to your scenario. Go back to the scenario and see what exactly they said that you may be not thinking of. So I know that we have used tangents, right? And even if I try to use this tangent, right, and I say that this tangent and the angle between the chord, right, if you have that angle there, it's going to be equal to the angle opposite, or the angle being supported by that same chord. That's not really that helpful in this situation, okay? It's not really that helpful because it doesn't really, find anything. So I've used the tangent for now, okay, for this question. It's not really helping me. But what about when they told us that NP is parallel to MO? NP is parallel to MO, right? What can we do with that? And how can we take a 30 degrees and include it, okay, in our answer? So we can use fun angles. And I see that if I use this angle of 30 degrees, and then I'm going to have to use this as the transversal line, then do you see that we have corresponding angles here? That's an upside down F, okay? So we have corresponding angles, so it means that angle N4 is equal to angle M. I'm going to state that. So it means that angle N4, or rather let's say angle M is equal to angle N4, which is equal to 30 degrees as well because of corresponding angles. Okay, so I'm also going to put that down and make sure that I let them know that is 30 degrees, just so that I don't get lost as I go on, because these answers may help you with your other questions as well. Okay, so those are 3 other angles equal to 30 degrees. That's 1, 2, and 3. Moving on to the next question. Then the next question, 8.2, says determine R and T. And it's for 2 marks, so it's probably just a 2-step process. That's it. Okay, so R and T. Well, R all the way to N, all the way to T, this whole angle. Well, the good news is we only have to find one angle in it. We have 30 here, we have 30 degrees here. We just have to find angle N. So how can we find angle N? That's the whole goal of this right now. Okay, I'd see that they gave us a diameter. I'm remembering that they gave us a diameter. This is a diameter. And that's why you see the context is very important. Always go back to it if you feel lost. So since this is a diameter, it means that the angle supported by the diameter in this circle is going to be 90 degrees. And so if you want to find angle N, it means that angle N2 plus angle N3 will give you 90 degrees. So how I'll find that, I'll just say 90 degrees plus angle N3, right? That's going to, not 90, sorry. It's not 90 degrees, it's 30 degrees. 30 degrees plus N3 would give you 90 degrees. So 30 degrees plus N3 is 90 degrees. And that's because of, you can say, angle in a semicircle. Then N3 would mean that N3 is equal to 90. And then you're going to take 30 over, which is minus 30, which is 60 degrees. So now that we know what N3 is, we can tell them what the size of that huge angle that they told us to find is. So that angle RNT is going to be equal to the addition of all these angles. So we can therefore say the angle RNT is equal to 30 degrees plus 60 degrees plus 30 degrees, which is really 60 plus 60, which is 120 degrees. So that would be RNT, and that's our angle. You don't really need a reason for this. This is addition, which is more of a fact than a theorem. Okay, so moving on to the next question. The next question, 8.3, says prove that, 8.3.1, triangle RNP is similar to triangle RTN. So let's highlight those triangles quickly. So they said prove that triangle RNP, so RNP, this triangle over here, we need to prove that that is similar to RTN. RTN. Well, the good news is you can see that they are sharing one angle. So one angle down, 2 more to go. Or really 1 more to go. Because if you get 1 more angle, 2 angles in the triangle are equal. By default, the 3rd angle is equal. Okay, so that already makes things so much easier. Okay, so I'm already going to start introducing the triangles. That's what we need to do to prove it similar. So I'll say in triangle RNP and triangle RTN. And what we're saying here is, do you see that they are sharing the angle R. So angle R is equal to angle R in both triangles. I don't have to say NR because it's R just on its own like that. So angle R equals to angle R, and you can call this a shared angle or common angle. I'll just say shared angle. So we're done with that. Then we just need one more angle because by default, the third angle will be equal. So let's see. In these two triangles, what other angle is equal? I see 30 degrees. See? 30 degrees here in this blue triangle is equal to the 30 degrees here in the red triangle. So I can tell them that angle N4 is equal to angle T, right? So angle N4 equals angle T. And it actually does go in the correct order because they say triangle RNP must be similar to triangle RTN. You see, RN, that's the 30 degrees. P, right? And RT, that's the 30 degrees N. So it does work, right? So angle N4 is equal to angle T. I'm just going to put that down. Angle N4 equals angle T. And so by default, I can call that WTO because remember they kept referring to that as WTO, right? So since we have that now, the third angle by default will be equal. So therefore, it finally just means, this one is already proven, not really given, but proven. So proven angle. And then the third angle is going to be equal. So just remember what the third angle would be. In this triangle RNP, it's RNP, this angle, P2. And in this triangle, it is RTN, the whole N, okay? Because that forms that whole N in that triangle they're speaking about. So really that angle that they spoke about in the previous question, this RNT, that angle RNT. Okay, so angle P2 is equal to RNT. That's what we're going to say. Angle P2 equals to angle RNT. And that is because that is the third angle in a triangle. If you like, you can say the sum of angles in a triangle. See, the thing is just that if you have two triangles and two angles in the triangles are equal, by default, this one is also supposed to be equal to that one. Okay, so now we have three angles being equal. Therefore, it means that triangle RNP is similar to triangle RTN, and this is because of angle, angle, angle. Okay, so that was a quite simple question. It wasn't that complicated. Moving on to the next question. Okay, and now we are on the last question for this paper. Okay, this question says we need to prove that, because that's what we're doing, prove that TW multiplied by Rn is equal to half of RT multiplied by NP. Don't get scared when you see questions like this. Remember, it's a follow-up of this question, right? They're both part of 8.3. So it means that this probably has a lot to do with the previous question. That's usually the case. It means that it probably has a lot to do with it. So first, you're going to take the sides that you see here. We see TW, I'm going to highlight that. I see RN, I'm going to highlight that. Okay, so first we're going to focus on the sides that we have. Because we have proven that these are similar, right? It means that they are now going to be in proportion. And this is what I mean by that. I'm not even going to look at the diagram to do this. I'm just going to look at this. This means that I can say Rn, right? If I take Rn over, and now in the other triangle, I have to also take the two corresponding sides. That's the first letter and the second letter. Those two sides, right? Over RT. Let me just put this all in red. It will be equal to, then I'll say NP, right, over TN. So NP over TN, because now we're saying they're in proportion since they're similar. And then lastly, that is equal to RP over Rn. Okay, and this is because we have similar triangles. They're in proportion because of similar triangles. Okay, now why did I do this? Because I want to see if these letters show up here. So I'm going to now see from here which letters are here. First, I see Rn. That's here. Okay, so I'll leave Rn. I see RT. That's also here. I'll leave that. So this two, they're going to work out. I'm going to leave them here. Then I see NP, right? The only thing I don't see TN, and I don't see this. And that's not a problem. That just means we're not going to use that part. As long as you can show them that one side of another side is equal to another side of another side, right? And it is in accordance with these triangles being similar, then you can actually do that because you're just saying that their sides are in proportion. So this is actually what's going on. The only thing that is missing is this. So let's piece it together. Let's think about how this happened. So first of all, what I'll do here is I'll take this, and because I can see that here they're being multiplied, that's why we have a dot here. I'm going to multiply these ones out. You see, it's a fraction and an equal to sign. So we're going to cross multiply. So it's saying, I'm saying Rn multiplied by Tn. So I'm going to have Rn times Tn. It's going to be equal to, and cross multiply here as well. That is RT multiplied by NP. Okay, so this is what I have right now. And you see that on this side, we have that little part. That's great. We have that part, right? The only thing that is different here is that half, first of all, that we see there, and this TW. And this is where we find out how this happened using the diagram. Okay, so I want to find out how did this happen? Why is there a half here? So in order to do that, since I have RT and NP, and I also have Rn, then it really means I just have to find out what exactly Tn is. Let's look at Tn and then just see, does it have any relation with TW and, you know, that half? So Tn, let's look at Tn. Okay, Tn, I'm already seeing something here. You see, look at this triangle. Now I want you to focus on this triangle because it has Tn in it, Tn. Do you notice that this line is parallel to this line? So we have a case of these two lines being parallel, and it looks like the proportionality theorem, but here's the catch, and this is why I can't say it's the proportionality theorem. Do you see that TO is a radius and OP is also a radius? So it means that this line is equal to this line. So this is not the proportionality theorem. What it is the midpoint theorem. This is the midpoint theorem. And here's why I say this is the midpoint theorem. So this is how the midpoint theorem works. You see, if you have been given a triangle, and let's call this triangle A, B, C, and then you are given a line drawn parallel to one side of the triangle, and let's call this DE. In the midpoint theorem, you will also be given that this line AD is equal to this line DB. Since we have been given this, okay, let me just write down what we have been given. We've been given that, first of all, DE is parallel to BC. And we've been given that AD is equal to DB. See, we've been given two things. What we would conclude is also going to be two things. What we would conclude is that AE is first of all going to also be equal to EC. It's equal to EC. And the second thing we conclude is that you see this lower side, BC, right? BC is going to be twice the size of DE. That's the conclusion of the midpoint theorem, right? So this is why I'm saying this is the midpoint theorem, because you can see that TO and OP, they are radii. And since we have that, those two lines are equal, right? But I can't just go ahead and just say, okay, I know they're equal. I have to tell them that they're equal. So let's write that down first. Tell them that OT is equal to OP. So let's go ahead and tell them that first because they're equal radii. OT equals OP because they are radii. Then the second thing we do is we look at this and we're going to say, since these two are equal, this would mean using the midpoint theorem that TW should also be equal to WN, right? Using the midpoint theorem. And of course that NP is actually twice the size of WO. I don't know if that one's going to be needed, but I'll just include it because it's the midpoint theorem, right? So I'm just going to say TW is equal to WN and the other one as well, W, okay? Twice the size of OW. Now that we have that, we can actually look at Tn and actually find out where it came from. Your reason for this one would be midpoint theorem. So you just say midpoint theorem, and I showed you above how the midpoint theorem works. Okay, now we can look at the work on this side really and just see where the Tn come from, because that's the whole point. I see everything else is present, everything is there except for Tn, and then I see this Wt, this Tw, and the half. So I want to know where it came from. Well, do you notice now that Tn, right, that full length of Tn is made up of Wt and Wn. Okay, that's a very important thing to point out. So look at what I'm just going to say here. I'm saying that Tn is equal to Wt or Tw and Wn. Those two, but we also know they're equal, right? So since we know they're equal, it means that Tn is actually equal to Wt or Tw plus, and in place of Wn, because I know these two are equal, I'm going to just call this Wn, I'm going to call that Tw, okay, plus Tw. And that would mean that Tn is 2 times Tw, okay? It's just algebra, we're just adding those two, so it's 2Tw. That's what Tn is. Okay, so because I saw Tw, I'm going to put it into my equation that I have here, and let's see how that works out. So in place of Tn. So I'm saying now that Rn is multiplied by, and in place of Tw, I'm going to say 2 times Tw. That is equal to Rt multiplied by Np. Okay, now that I have this, how does it get to look like this? Well, everything seems to be there right now, even if we just like take this and just put it here. Let's compare them and see what is missing now. We have Rn, we have Wt, right? We have Rt, we have Np. But we still have a 2 here. That's not an issue. The 2, if we just decided to divide both sides of this equation by 2, we can get it to come over here and to be a half. So this is what we're doing. We're dividing both sides by 2. And so this means that we have here, the 2 cancels. You have Rn, right? You can put it in the same order if you want, because you have Wt here. See, Wt. So I said Wt first, then multiply by Rn, which we have left. The 2's cancel, is equal to, and then look at how I can rewrite this. You see, in front of Rt, you have a coefficient, an invisible coefficient of 1. So you can write that as that 1 over the 2. So that's 1 over 2. Multiplied by, so 1 over 2, and then it's a coefficient of Rt. So I can just say Rt multiplied by Np. And that's how they got that. So you see, it's not a guessing game. It's never been a guessing game. You look at what they give you, you look at the previous question, usually helps, and then you start seeing the pattern. Like, I saw what was here that was also in the proportions of that. And from there you move on and you're able to actually find a way to get to the answer. Never just leave it empty, because you're going to get marks for your steps. Okay, so that is the end of this video. This paper was for 100 marks. So I hope you guys enjoyed this video. If you have reached the end of this video, thank you. And if you like this video, please make sure to like and subscribe for more content like this. And I will see you guys in the future videos. Bye for now.